of your prep session for APSC 112. Hope you had a good Saturday night, just the right amount of fun, and hope you're all set for another 4-hour session of physics. By the time we finish today, we will have finished covering magnetism, magnetic force, magnetic field calculations, and we will have covered electromagnetic induction. And so heading into your final exam, by the time we finish today, you're going to feel a lot more confident, especially with that material. In your course booklet, I'm just going to flip back to page 8 and the outline for today. You don't necessarily need to flip to that page. If you want, you can just look on the screen here. And just showing you the game plan for today. So we've got 4 hours today. Again, we're not going to do a full 4 hours straight of physics. I've got 2 nominally 10-minute breaks set up for us. And what I want to do with our first hour and 15 minutes here today is just finish our review of magnetic force and magnetic field. And we're going to go through a couple of long answer problems that I think are good for us to study from. We'll see an example of how to use the Biot-Savart law to calculate the magnetic field created by an object. And we'll look at a more complicated long answer problem as well, involving a mixed kind of force and field calculation. And then with the remainder of the time after our first break, we're going to get into electromagnetic induction and Faraday's law and spend lots of time practicing that and just wrapping our heads around that concept, what it is, how to recognize it, how to solve those problems. So that's the game plan for today. Just before we dive into some long answer problems, let's go back to page 198, 199 of your booklet. So let's start on page 198. And just to highlight this section in your booklet again, section 7.12 on page 198, what I've done there is summarize the 5 main kind of manifestations of magnetism that we need to understand. And essentially you could view these as problem types. These are the types of questions you might run into. Lots of words there. I won't go through that in lots of detail, but on page 199, I've summarized kind of the same information, but in a different way. And so you can see in the leftmost column of that table, just the phenomena or the description of that manifestation of magnetism. And we noted yesterday when we talked about the force on a current carrying wire, or the corresponding torque on a loop of current carrying wire, or the force on a moving charged particle due to an external magnetic field, we listed those as effects of magnetism, right? That's where there's some external magnetic field, maybe it's a horseshoe magnet or whatever it is, but that external magnetic field has an effect on some object. We listed the corresponding force and torque equations and the right-hand rule, the corresponding right-hand rule for each of those effects. And then we looked at what causes magnetic fields. And we're going to practice a long answer problem on this, on the Biot-Savart law, which is how do you calculate the magnetic field created by a current? And then finally, kind of the combination of both of those things, the forces exchanged between 2 long parallel current carrying wires and the notion that opposites repel. This formula that we looked at yesterday, we discovered is not on your formula sheet, but we derived it in the problem we solved, and we saw that it's pretty easy to derive. It's really use the equation for the field created by one current and use that to calculate the corresponding force on another current. All right, so that's a quick summary of where we got to yesterday with magnetism. I just want to look at one more thing that we should review briefly, and let's go to page 200, the next page. You'll find page 200 should be a blank page for notes. And what I want to cover there is the Hall effect. And I don't have a section dedicated to the Hall effect in your course booklet this year. This topic was actually historically not covered explicitly in APSC 112, and as far as I know, they just added it. So I don't have any problems on this topic for you, but I'll walk you through what the Hall effect is, and we'll look at the formulas, and we'll see that, in fact, it's kind of similar to a velocity selector. So let's just walk through that, a quick review of the Hall effect. And to understand that, I'm going to draw a picture here, and it's a picture of a macroscopic material. this is some kind of conducting material. You could consider this like a slab of copper, for instance. This material has a width and it has a length. And we should probably give some coordinate axes to this. So let's assign some coordinate axes here. X, Y, Z, that's a right-handed coordinate system. Okay, and what we're going to do is attach a battery to this material. And if that material has some finite resistance, then it would cause a current to flow. So let's label a current on here. And the way we've connected the terminals of this battery, that should cause a current to flow this way into our material. So here's the interesting thing to consider. This looks just like a resistor and a battery, right? Just like a normal circuits question. But what we should consider is what happens if there's a magnetic field? What happens if we put such an arrangement in an external magnetic field? And let's say that we've oriented that external magnetic field such that it's in the Z direction, upwards. Okay, so we brought a magnet nearby this arrangement to cause this magnetic field to influence what's happening. And then at a microscopic level, if we zoom in on one electron in that material, what's that electron doing? Well, if there's a current flowing in what we've labeled as the positive X direction, that's conventional current, right? And so that electron would normally be tempted to travel in the negative X direction. Let's just call that a velocity, a drift velocity in the X direction, but it's actually an electron traveling in the negative X direction that we've assigned. So that's normally what would happen, but if we have this magnetic field, we know that there's a force acting on a moving charged particle. And we could use the right-hand rule to figure out the direction of the force on this moving electron. So remember Q, V cross B, take the fingers of your right hand, point them in the negative X direction, in the direction that that electron would normally travel, and curl your fingers into the direction of the magnetic field, which is in the Z direction. And that would give a force on a positive point charge in the positive Y direction, but electrons are negatively charged, so the resulting force is actually in the negative X direction. So this is the magnetic force that acts on that electron. That's just by virtue of the fact that it's moving and there's a magnetic field present. So what happens? Electrons tend to gather on one edge of this material, and they leave behind a net positive charge on the other edge of the material. Just by virtue of putting this arrangement in a magnetic field, we're causing a separation of charge in that conducting material. And anytime there's a separation of charge like that, well, that creates an electric field and a corresponding potential difference. And so if you were to connect an ideal voltmeter to this arrangement, I know that my diagram's getting pretty messy here, but what you would find is that there's a corresponding, what we call Hall voltage, that develops across the width of that material. And so I'll just try to summarize that in equation form and some words down here. And by the way, you can see a much cleaner picture of this probably in your course notes or your textbook, or even on Wikipedia. If you just Google search the Hall effect, you'll see a much neater picture of that. That's just us talking through what's happening. Okay, so for an electron, F equals QV cross B. And what we noted is that electrons are deflected to one edge of that material. But as electrons get deflected to one edge of that material and they get separated from the corresponding positive charges, or holes, you might consider them, on the right side of that material, there's an electric field that develops, a potential difference that develops. So there's a combination of electric and magnetic forces that act on those electrons. And so in equilibrium, the magnitude of the magnetic force will equal the magnitude of the electric force. I guess for clarity, let me just highlight that, right? This is the magnetic force and this is the electric force. So once some kind of equilibrium is reached here, then QE equals QV cross B. Remember, this looks pretty similar to what we saw for a velocity selector, right? It's not actually that different. And what you end up with is an electric field that develops in the y direction with a velocity in the x direction and a magnetic field in the z direction. And that formula is actually exactly the same as what we had for a velocity selector. And this thing here, the speed of the electrons, is also corresponding to the drift velocity of those electrons as they move through that material. So we can take this a little bit further. That electric field that develops across the material in terms of the drift velocity and the magnetic field, we could express that in terms of a Hall voltage across a certain width of the material. We could invert that to solve for what the Hall voltage is. And we could even go one step further and express that instead of in terms of a drift velocity, we could express it in terms of the corresponding current that flows. So that's a consequence of the drift velocity. Now, this formula is not on your formula sheet. You could see that you could derive it from this one, right? The same equation that we know for a velocity selector, and just sub in for Hall voltage acting across a certain width of material, so electric field and potential difference across a certain distance, right? And then if you really wanted to sub in for the corresponding current instead of the drift velocity. What do we use this for, and why do we care about the Hall effect? This is used to build magnetic field sensors. And typically we use a semiconducting material, one whose resistance we know really well, and whose electrical properties that we know really well. And by measuring the voltage that develops across that material and the corresponding current that flows through the material, we can estimate what the magnetic field is. So that's the Hall effect. Like I said, I haven't seen questions on that from previous year's exams, but I know you guys covered it this year and it hadn't been covered in previous years. So that's a little bit of a heads up, a little bit of a review about it. I'll just pause there and see if there's some questions. Yeah, so first of all, what is W? W is the width of the material. I'll just try to label it on this somewhat messy diagram for you, right? W is the width, like in units of meters of that material. And the reason that this is an effect, the reason this happens is because that material has a finite width. There's also some questions. What is NTE? I'll just scroll down again and highlight where that came from, right? So here's the drift velocity. And if you were to substitute in the equation for the drift velocity that relates drift velocity to the current, this is the number density of electrons. So that's electrons per cubic meter. This is time, and this is the charge on an electron. And just for clarity, I'm going to highlight that formula on your formula sheet for you. Just bear with me one sec while I zoom in here. I think it's on the second last page of your formula sheet. And it's right here. That's an equation for the drift velocity. And it's in terms of the current density, which is the current divided by the cross-sectional area of the material. And from that, you can get that equation that we just derived. So N, again, is what we call the number density. So in essence, that's number of electrons per cubic meter of material. And the reason that we build Hall effect sensors out of a certain semiconductor material that we know really well is because for semiconductor materials, we know exactly what the number density is of a certain material. Silicon germanium, for instance, is one commonly used semiconductor. Okay, yeah, so where does the W go? The W goes into solving for the relating the drift velocity and the cross-sectional area of that material, right? So cross-sectional area is the width of the material. Okay, let me try to highlight that on the other page for you. So let's highlight that. I'm going to just label these quantities. This is the drift velocity. That's obviously the drift current. That's the number density. That's the thickness of the material. And that's the charge on an electron. So the highlighted items that you see there come from the equation for current density drift velocity. And if you consider that the cross-sectional area of that conductor is the width times the thickness, that's where the A goes from that drift velocity formula. Okay, so that's the Hall effect. I don't have any questions for us to practice on that. But if you want, when you're studying, what you might want to do is just make sure that you can get from this equation, which is the velocity selector equation, make sure you can get from that to that last equation for the Hall voltage. And then I think you'll be in good shape if you run into a Hall effect question on your exam. Okay, I'll just pause there and see if there's any other questions. Okay, I think we've addressed all these questions. And again, my diagram, like I'm not great at drawing at the best of times, especially on my tiny little tablet here. That diagram's not super clear, but you can find diagrams of this definitely in your textbook, most likely in your course notes, and even on Wikipedia, there's a decent diagram just like this. All right, so that's the Hall effect. All right, let's get into some more long answer problems on magnetism. We're going to spend the rest of this period before the break just working through a few long answer problems. So to do that, let's start on page 227 of your booklet. We're going to page 227, and there's some room there to look at the problem that's on page 51 in your exam package. Page 227 and page 51. And once you find that problem on page 51, it should look like this one. I'm going to give you a couple minutes to read that one over. Okay. Anytime you see the words current carrying wire on your exam, right away you should be thinking about magnetism or induction. And in this case, we're told that there's a current carrying wire. They highlight the current and its direction in this wire. And it's in a region where there's a magnetic field out of the page. And in part A and B, they tell us to ignore the magnetic field produced by the current in the wire itself. In part A and B, what we want to do is solve for the direction of the net force on this wire. And in part A and B, solve for the direction and the magnitude of the net force on the wire. So in this case, we're asked to figure out the effect of a magnetic field on something, right? We're given a magnetic field B and this arrangement of current carrying wire. We want to find the force that acts on the wire. Okay, and then in part C, it says, now suppose the background magnetic field is turned off. Indicate the magnetic field produced by the current in the wire in the plane of the page. So part C is like talking about the cause of magnetic fields, right? Here's an arrangement of current carrying wire. What magnetic field does it create itself? So let's treat part A and B separately from part C. And let's take a look at part A and B. Back in our course booklet, I'm just going to reproduce that diagram for us. And let's label some things on this diagram. So there's a certain length L of wire on either side here. And the arc of wire has a certain radius. Let's call it big R. There's a current that's flowing in the wire, little I. And there's a magnetic field that's coming out of the page everywhere. And effectively in parts A and B, we want to solve for the magnitude and direction of the force on this. So in general, we're looking at the force on a current carrying wire. We've got a formula for that. It's F equals I L cross B. And that works if we have straight wires. Or maybe saying it differently, it works if we have wires who have a consistent direction of current. That little L vector is kind of like a combination of the length and direction of the wire carrying the current with respect to the direction of the magnetic field. But in this case, we don't have that because of that arc part of the wire. We could figure out the force on each of the straight segments, but separately, figuring out the force on the curvy segment is going to require us to consider that this has got some shape to it. We're going to have to add up the bits of force that act on each segment of that curved part of the wire. So we could label on our diagram, if you want, there's a little DL vector here in the straight segment. And similarly, we could pick a segment of the curved, the arc of the wire, call that DL, the little DL vector. And if you wanted to figure out the bit of force on the DL in the straight segment, it would be straightforward because every segment of that straight wire has the same orientation relative to the magnetic field. But consider that different segments of the curved portion of the wire have different orientations with respect to that magnetic field. So we're going to have to consider the bit of force. Let's call that bit of force dF that acts on each bit of that curved segment of wire. Oh yeah, there's a couple questions that came in here. For part A, don't we only need to figure out the direction? Well, you're right. For part A alone, we just need to figure out the direction, and we could do some right-hand rules. But for part B, we're going to have to figure out the magnitude as well, right? So we're going to have to go through all this anyway. So let's just set it up from the beginning this way. We've got to figure out the magnitude and direction of the force on this wire. And we have to do an integral to figure out the magnitude of the force on the curved part. So if we consider breaking up this whole thing into little segments of wire, and now consider each segment separately, for the straight segments, let's figure out the direction of that force. I, the current, goes right to left across the screen, and B, the magnetic field comes out of the screen. And so if you do the right-hand rule, fingers in the direction of the current, curling out of the screen in the direction of the field, you get a downwards force on any portion of either of those straight segments. So we could figure out the force on the straight segment straightforwardly, right? We don't even have to do an integral to do that. We could just multiply by the length. So that part's straightforward. Let's just take a note of that. And I'm just going to correct that on each straight segment. I guess we could label that even F straight, I guess, is I times L times B. And we could even assign that a direction if we wanted to in a coordinate system, or we could just call it down. That's probably sufficient. And now when we look at the curved portion, we're going to have to somehow account for the varying direction of all the DLs around that curve relative to the direction of that magnetic field. Let's just do a little bit of geometry here. Let's call this angle theta. And let's call this angle phi. And if you look at that cross product of vectors, we could either look at the cos phi component, like the horizontal component of DL, or we could look at the sine theta component. Either of those is going to result in a vertical component, df subscript y, downwards. And so for the arc, df subscript y, the y component, is going to be df, and it's either going to be the cos phi component or it's going to be the sine theta component. We can choose whichever one works out a little bit easier math-wise for us. And the total force in the y direction on the arc is going to be the integral around the arc of that. And we'll choose which one, whatever makes sense for us. So that's the y, or the vertical, I guess the vertical component of the force on the arc. What about the horizontal component of the force on the arc? Consider that if you consider a given DL on, let's say, the left half of the arc, right? It's kind of pointing upwards and then making its way to horizontal, right? The horizontal component of the force is going to depend on kind of which DL you consider. But then consider that when DL comes back down the other half of the arc, the horizontal component of the force is going to be the opposite. So there's some symmetry here. For any DL on the left half of the arc, the horizontal component of the force dF is going to cancel with the corresponding dF from the other half of the arc. So we can make a note of that. In the x direction, all the dfx's cancel. So the horizontal component of the force on the arc is 0. There's a question in the Q&A, how is the force down? Well, we're just saying in general, right? As you can see from the way I've annotated the picture of the arc, I'll just highlight it here. A given DL has a resulting force acting on it. Remember, the force is at right angles to the DL and to the magnetic field. The magnetic field's out of the page for all parts of that arc, but the DL is changing direction. So the DF is changing direction as we consider different DLs. The horizontal components of all those DFs cancel out as you consider all the different DL directions, right? But the vertical components, there's always going to be some vertical component. In the extreme, that vertical component will be 0, or it'll be purely downwards. But there's always going to be some vertical component there. Okay, so we're going to have to do that integral. And what we have to do is somehow express what that df is in order to do that integral. So what is df? According to that vector cross product we have up near the top of the screen, right? The magnitude of that df is I B dl. And the vectors and the cross product have gone away, and the reason is that dl is perpendicular to B for any dl on the page there. And now we need to express dl in terms of some way of accounting for where it is on the arc. And we've labeled 2 different angles, either theta or phi. We can choose whichever one we want. But consider that dl, in terms of arc length, is big R times, let's use d theta. I'll just denote that on the diagram for us. There's a little d theta here, right? We consider that dl is actually made up of a infinitesimal angle. So we could sub that df into our equation, and we can get an expression for the integral, the total vertical component of the force on this thing. In terms of thetas and d thetas, it should be I B R sine theta d theta. And in order to count for all the dl's that make up that arc, what is the integral of theta? What are the bounds of theta that we're integrating? We're integrating from theta equals 0 to pi. And as we sweep theta from 0 to pi, we'll be sweeping through that half circle and adding up all the bits of force in the vertical direction acting on the arc. And the integral of sine theta d theta is minus cos theta. So we already know the answer to this. It's minus I B R cos theta, evaluated from 0 to pi. If you calculate cos pi minus cos 0, you get 2. So the result is 2IBR. I'm just going to pause there for a second, see if there's any questions about how we set up that integral or evaluated it. So we've figured out an expression for the total force acting in the y direction, downwards on the page, on that arc. And now we need to express our overall result. So let's flip over to the next page to do that. I'm just going to, I guess I have a bit of room down here at the bottom. I'm going to do it here. So for the entire wire, the net force is it's going to be 2 times the force on each of the straight segments, so that's 2ILB, plus it's going to be our result for the net force acting on the arc, that's 2IRB. And all of those forces are acting in the y direction, so you could call that minus j hat if you want. If you labeled on your diagram, you could even just call it down. That should be enough to get full marks. Just catching up to a couple of questions on the Q&A here. We've assigned a direction for the force, right? We've realized that on the straight segments, there's no horizontal force, it's all downwards. And for the arc segments, all the horizontal DFs are going to cancel out when you consider the left and the right half of the arc. So there's a net force down on the arc. There's a question about the difference between, I guess, I and big I. I'm just struggling to see where that is. Oh, sorry, let me just highlight that. So this is the general formula, just highlighting at the top of the screen here, right? This is the general formula for force on a current carrying wire segment. And it's listed in terms of the current big I. That's what you would find on your formula sheet, right? If you looked at it. In the question, for whatever reason, they denoted the current on the wire as little I. And so everywhere in our math down below, we've been expressing it in terms of little I. That's the only reason for the discrepancy there. All right, just check in on some other questions here. Yeah, so this is a good one. Will the force always be perpendicular to L, the length of the wire? Yeah, it will. And I'm just going to highlight that on the screen for us. Bear with me for 1 sec while I clean up a few of these highlights. Just focus on the highlighted equation in the top left of the screen. So that's the general equation for the force on a current carrying wire segment. And that's a vector cross product. Just mathematically, that vector cross product says that the direction of the force is perpendicular to both the direction of the current and the direction of the magnetic field. Now, this notation can sometimes be confusing for people, right? But really, like, what is IDL? It's the magnitude of the current multiplied by a little direction vector that says what direction that current is pointing in for whatever segment of wire we're considering, right? So it's kind of like that whole first part of the vector cross product, the IDL, is a vector itself. And so that equation is saying the force is perpendicular to both the current, which is in the same direction as the wire segment, and the magnetic field. Hopefully that answers your question. What does the direction J hat mean? Yeah, so you guys might have your own notation for this, but and we were a little bit sloppy, I guess. We didn't assign a coordinate system here, right? But if you wanted to, you could have assigned like an X and a Y coordinate system like this. J hat is a unit vector that points in the negative. Well, J hat is a unit vector that points in the Y direction, and minus J hat points in the negative Y direction. So that's unit vector notation that you've probably used. I'm pretty sure you've used that in your course. There's a question here, where did the second 2IBR come from? There should only be one 2IBR in our equation. The 2 itself came from evaluating that integral, right? So just to highlight here, right, we have a negative sign minus cos theta evaluated between pi and 0. So if you evaluate cos pi minus cos 0, you should get minus 2, and then the negatives end up canceling out. This right here is the net force on the arc itself, but for the entire wire, right, there's the arc and there's the straight segments. That's where that 2IRB came from. All right, and just catching up to some other questions here. Yeah, so in terms of the directions of the forces on these things, let's just take a look back to the picture, just to make sure we're comfortable with the directions of the net forces on these things. Just consider one of the straight segments, and consider either one. It doesn't matter which one you consider. Let's figure out the direction of the force on either of the straight segments. So using the right hand rule, put your pen down if you're right-handed, fingers in the direction of the current, so left to right across your page, curl your fingers of your right hand into the direction of the magnetic field. The magnetic field points out of the page. I'm going to try really hard to do this on camera for you, but it's always a little bit tricky for me with perspectives here. Okay, so here's my fingers, and I'm trying to point them left to right, I guess, from my perspective on the page, right? And then I need to curl them out of my page towards me, right? And if I do that, my thumb points down. It's near impossible to see this on the camera. I'm looking at myself over here, and it's really hard to get the perspective right. If I were in front of you guys in a classroom, I'd be doing all kinds of gymnastics for you. But consider this, right? If you point your fingers from left to right across your page, I'm going to try to highlight this. There's lots of different ways to orient your hand with your fingers pointing in that direction, right? Like you can twist your hand all the way around and keep your fingers pointing that way. But there's only one way to point your fingers that way and then curl them out of your page towards you. There's only one way to orient your fingers, pointing that way and then curling them out of the page towards you. And when you do that, your thumb points down. Hopefully you guys can see that on the camera. It's a little bit of gymnastics for me, but hopefully that helps to figure out the direction of the force on the straight wires. Now you could make a similar argument for any of the arc segments. And for the arc segments, consider that little vector dl, in the extreme, it either points perfectly horizontally or perfectly vertically. But for most segments on the arc, it's somewhere in between horizontal and vertical on your page, right? So there's going to be an x and a y component of the force from acting on each dl vector. And when you consider all the horizontal components, what you find is that when you look at the other half of the arc, where all the dl's are pointing angled downwards, all the x components cancel out. Maybe I can show that a little more clearly here. Consider a dl over here. What force components are there on it? And you know what, just for the sake of this discussion, I'm just going to try to draw an even bigger picture over to the right here. Consider a dl that's kind of upwards on the left half of that arc, and consider the components of the force on it. So dl cross b out of the page will give a force kind of down and to the right. So there's going to be a dfx and a dfy. But now consider the force acting on the dl on the other part of the arc, when the dl's are all angled downwards. There's still, oh guys, sorry, hang on. Let me just correct this, right? The force acting on dl on the left half of the arc has a vertical component and a horizontal component, and the vertical component points downwards, like so. Let me clean this diagram up a little bit to make this hopefully more clear. Okay, hopefully that's clear. The force acting on a dl on the left side of the arc looks something like that. But let's go through the same exercise for the dl on the right half of the arc, where the dl is kind of angled downwards. So dl curled into the magnetic field vector is a df that's somewhere like this. And that df has horizontal and vertical components to it. It has a vertical component like this, and it has a horizontal component like this. And so what you can see is that all the horizontal components cancel out with each other when you consider the left and the right halves of the arc, but all the vertical components add up. Hopefully that's clear. I know there's lots of little vectors in there, but hopefully that's clear for seeing that. Okay. Now we still have to look at part C. And part C says, now imagine we switch off that background magnetic field. What's the direction, or what is the field created by the wire itself? And so I'm gonna draw our wire again. And there's an L here and an R here and an L here. And just before we set about trying to answer that, I'm just gonna flash the question back up. And we should read the wording really carefully. So focusing on part C here, suppose the background field is turned off. Indicate the magnetic field produced by the current in the wire in the plane of the page. So just pause for a sec. The magnetic field created by that arrangement of wire depends on where you are, right? It depends on how far away you are from the wire. It depends on where left and right on the page you are. It depends on a lot of things, but they don't specify a location. They don't say at the origin. They don't say, you know, at a particular place on the page. They just say indicate what it is. So I think what they're asking us to do is just tell them in a general sense, what does the field kind of look like created by this arrangement of wire? So let's go through that exercise. And I'm going to go back in my booklet to try to help us do that. Field created by the wire arrangement. Each of the straight segments of wire is going to create its own magnetic field around it. Let's do those ones first. So for the magnetic field created by a long straight wire, remember the straight is mu naught I over 2 pi r. And the right-hand rule that we use for that is we point our thumb in the direction of the current and our fingers curl around the wire to indicate how the magnetic field vector is curling around the wire. And in this case, the current is flowing like this. So let's consider the leftmost straight segment and consider the field created by it. There's a current flowing straight left to right. Point your thumb left to right. Everywhere above that wire in the plane of the page, the magnetic field created by that straight wire points out of the page. Your fingers curl around such that they curl up out of the page towards you, everywhere above that wire, and then curl your fingers over, and everywhere below that wire, they curl back into the page. So let's highlight on our diagram that for the straight part of the wire, there's a magnetic field, let's call it B straight, that comes out of the page and then back into the page. And of course, the magnitude of that vector depends on how far away from that straight segment you are, up or down in the plane of the page. And a similar thing happens over here, same argument. Now let's consider what's happening with the arc. So for the arc, consider that the arc is made up of a bunch of very infinitesimally small straight segments. And if you were to point your thumb along the arc, the direction of your thumb would keep changing as you kind of swept your way around that arc with your thumb. But consider that no matter which segment of that arc your thumb is pointing along, your fingers always curl such that everywhere above the arc, they're curling out of the page, and everywhere below the arc, they're curling into the page. So we could label that on our diagram as well. it would be something like this. And no matter which segment of the arc you consider, no matter which segment of the arc your thumb is tangent to, that would be true. And so if you take the vector sum of all those magnetic fields, what you find is that everywhere above the wire, the net magnetic field is out of the page. It has a different magnitude depending on where you are above the wire, but everywhere above the wire, it's out of the page. And then similarly, everywhere below the wire, it's into the page. So the way to get full marks on this is probably to say something like that picture, and also to say everywhere above the wire arrangement. B is into the page, out of the page. And then everywhere below the wire. The magnetic field is into the page. Now, this question really highlights how important it is to read carefully the wording of the question, because the wording of the question doesn't specify a location. It just says indicate what the field kind of looks like in the plane of the page. If they had asked you, what is the magnetic field at, for instance, point O at the center of the arc? Well, then you'd have a definite location where you'd have to do a calculation to figure out the magnetic field, but it didn't specify a location. And we know that the magnetic field created by each of these wire segments depends on how far away you are from that wire segment. So without specifying an exact location to do a calculation, you can't calculate it. So all they were looking for was kind of a subjective answer there, and we did our best to answer it subjectively. This again really highlights the importance of reading the question slowly and carefully. They didn't specify an exact location, so we couldn't do an exact calculation. And this should be enough to get us full marks on this. Yeah, there's a good question in the Q&A. So what's the general formula for the magnetic field created by a curved segment? And I'm glad you asked. It's a good segue to our next question. We're going to do exactly that in our next long answer problem. So let's go to page 229 of your booklet. And on page 229, there's some room to look at the long answer problem from page 52 in your exam package. Page 229 and page 52. So it's basically the next page of both your booklet and your exam package. And once you find it, it should look like this. Take a moment and read that one over. All right, so we've got a circular loop of wire, and it's carrying a current little I. And you can see the little I going around the loop here. Consider a point P along this vertical axis of the loop, a certain distance Z above the center of the loop. And in part A, what's the direction of the magnetic field at point P due to the current in the loop? And in part B, it's not really labeled part B, but kind of assuming that's part B, what's the magnitude of the magnetic field? So before we dive into any math here, let's just pause for a sec. Part A is about the direction of the field. And we might be able to use the right-hand rule and some reasoning to get us an answer to that. Part B is about the magnitude of the field. And to get an answer to that, we're going to have to use the Biot-Savart law. So we're going to treat this as a Biot-Savart law question. We're going to use the Biot-Savart law to calculate both the magnitude and direction of the magnetic field at point P. Once we finish all the math on that, we're going to kind of zoom out and extract ourselves from the math and revisit the way these marks are distributed. And I'll just show you how you could get the 3 marks without doing any of that math. Okay, so let's head back into our course booklet and set this problem up. All right, so we've got a vertical axis here, and this is labeled, I guess, as the Z direction. So here's point P, and here's our loop. The loop has a radius of R, and point P is a distance Z above the plane of the loop. And so our job is to figure out the magnetic field at point P created by that current in the wire. Okay. Now, the Biot-Savart law, I'm just going to write it over on the right here for our reference. This is what we need to use to calculate the magnetic field created by any arrangement of current carrying wire. And the Biot-Savart law has 2 different forms. It can be written 2 different ways. Mu naught I over 4 pi dl cross r over r cubed. It can also be written like this. dl cross r hat over r squared. And I'm just going to highlight once more the difference between those 2 equations. There's actually no difference at all. The vector r divided by its length is the same thing as r hat. So notice that one of those denominators has r squared and one of them has r cubed. You can use either formula that you want, but personally I prefer to use the second one. And the reason is that this is a unit vector. And that r hat vector points from the bit of wire dl to the point P. And it just makes the math a little bit easier if that's a unit vector. So let's label some of these things on our diagram. What we want to do is figure out the bit of field at point P created by a little bit of wire dl. Let's consider this bit of wire. That's dl. There is a vector that points from that dl all the way to point P. That's the vector r that's in the first form of that equation for the Biot-Savart law. There's also a unit vector that points in that direction. That's r hat. Okay. Now, the Biot-Savart law says that if you look at the vector cross product here, the Biot-Savart law says that the little bit of field points perpendicular to both dl and r hat. So using our right hand, what's perpendicular to both DL and R hat? It's a vector that points it's really hard to show this in perspective. I'll try my best. It's a vector that points something like this. That vector is perpendicular to both DL and to R hat. It's really, really hard to show that in perspective on the screen here, but hopefully you can see that, right? Take your fingers and curl them, point them along DL, curl them towards R hat, and your thumb kind of points diagonally away from both of them. And so on our diagram, we could label that, right? The bit of field that we're interested in calculating is something like this. That's the bit of field created by that little segment of wire, DL. Now, what happens if you consider a different DL? What happens if you go all the way around, halfway around that arc, somewhere, I don't know, over here, let's say? There's a different DL, and that DL's R hat points like this, and that DL R hat result points something like this. So there's a different DB that points up there somewhere. Okay, so what happens when you consider all the DLs around that arc? You almost get like a cone of DB vectors up at the top there at point P. Those are all the little magnetic field contributions of that entire arc of current carrying wire. And what happens if you take the vector sum of a cone of vectors like that? All the horizontal components cancel out and all the vertical components add up. So what we need to consider is only the vertical component of that DB. We can make a note of that on our page here. And I guess maybe even for completeness, we should probably label some axes on our page. So bear with me one sec while I annotate that. We could say that in perspective, there's X, Y, Z coordinates on our page. And we could write in words that from symmetry, sorry guys, my tablet. From symmetry, all X and or Y components of the magnetic field cancel out. And only the Z component survives. And in fact, add up. So what we're going to need to do is somehow express the vertical component of that. And we could use an angle theta to do that. So here's an angle theta. And that means that this is also an angle theta. And so the Z component of any dB is the sine theta. Did I get that right? Hang on, I don't think that's quite right. The Z component is the sine theta component. We just need to make sure we get this right on our diagram. that's the component that we're looking for. Nope, sorry guys, I got that wrong again. I got my perspective all twisted around on my diagram here. That angle is in fact theta, and it is the cos theta component that we're interested in. And so it's the cos theta components of all those dBs that we're interested in. So let's start again with our Biot-Savart law. So dB is mu naught I over 4 pi dl cross r hat divided by r squared. And the z component of that is the cos theta component of that. Now let's try to simplify this a little bit. Cos theta should be adjacent over hypotenuse, right? And the other thing to make note of is that the magnitude of dl cross r hat is equal to 1. And the reason is that those are both unit vectors. And that's why I like using the r hat form of the Biot-Savart law equation. And so if we substitute those results in, the z component of that bit of field we're looking for is mu naught I over 4 pi. Cos theta is big R over little r. And there's a 1 over r squared there. And that whole thing simplifies down. Oh, guys, sorry. Let me highlight something. Sorry. What's the magnitude of dl cross r hat? It's not 1. Sorry. It's dl. And we can simplify that one step further. This is r dl over little r cubed. Okay. I'll just pause there and see if there's any questions. I'm going to just highlight in big red letters, cross this out, right? The magnitude of dl cross r hat is dl by definition. There's a question, why is cos theta big R over little r? So if we look at the diagram, it's going to get kind of messy here. I'm just going to temporarily highlight this triangle for you. The hypotenuse of that triangle is a vector little r. And by definition, in the Biot-Savart law, that points from the bit of wire creating the magnetic field to the place where we want to calculate that magnetic field. So the hypotenuse of that triangle is little r. And if theta is the angle down in the bottom here of the triangle, then cos theta is adjacent over hypotenuse. All right. The trick is setting up all these integrals, but once we've got them set up, evaluating them isn't actually that hard. So the net magnetic field at point P is the integral of all those Z components that survive. A bunch of those things are constants. Mu naught I r 4 pi. Little r itself is actually a constant if you consider that any dl is the same distance little r from point P. And really what we're doing is integrating around the length of that wire. And what's the integral of the arc length around a circle? It's the circumference of the circle. Mu naught I big R over 4 pi little r cubed times 2 pi r. And that's big R, the radius of the circle. Now we could simplify that a little bit further. Notice that, so big R is the radius of the loop of wire. And we were given that in the problem. So we have to express our answer in terms of big R. But little r is a variable that we created. It's the distance from any DL to point P. And we should try to express that instead in terms of big R and Z if we could. So let's just make a note of that. Little r from Pythagorean theorem is Z squared plus big R squared. Okay, I've run out of room on my screen here. I have to flip over to the next page, but what we're going to do on the next page is just rewrite our solution, and we're going to sub in for R here and simplify some of those big R's just to clean up our solution. So you guys are good at algebra. I'm going to flip the page away. Don't panic when I do that. We're just going to simplify that one more step. And so the magnetic field at point P becomes mu naught I big R squared divided by 2. And instead of the little r, we've got Z squared plus big R squared to the 3/2. Now this is written in terms of a big I, which is what appeared in our Biot-Savart law equation. I guess if we really, really wanted to, we could express that in terms of little I, which was given in the question. It doesn't really matter, it's the current, right? We could write it like this if we wanted to get it in terms of everything that they provided in the equation. Now, let's just pause and zoom out from all that math for a second and make sure that we're comfortable with this. What we've done is calculated the magnetic field, a distance Z, above the center of a loop of current carrying wire. And we should take a note that if Z equals 0, so i.e. at the center of the circle, or center of the loop, and in the plane of the loop, the magnetic field reduces to this, mu naught I big R squared over 2. Now if Z is 0, what does that turn into? That turns into mu naught I over 2R. Now that's the magnitude. We know that this vector points in the Z direction. So if you want, you could write this as K hat, or if you want, you could write this as Z hat. It doesn't matter how you label it, but it's in the Z direction from our diagram. And this equation at the very bottom is what we call a special case for the magnetic field created by a loop at the center of the loop. And I'm just going to write one more thing here. Compared to the magnetic field for a straight wire, which is mu naught I over 2 pi R. This big R is the radius of the loop. And this little r is the distance away from the straight wire. And there's a pi in the denominator as well. So the point I'm trying to make is that these formulas look very, very similar, but they're not the same thing. We've got an equation at the top, which is for the special case of a loop, where we're calculating the magnetic field at the center of the loop. Whereas the equation at the bottom is the magnetic field created by a straight wire, a distance r away from the straight wire. And there's a pi in the denominator. So they're not exactly the same, even though they look very similar. Okay, I'm just going to pause for a sec here. Let's zoom out from all that calculus and all that math and just take stock of what we've just done. Okay, I'm going to flip back to the previous page. And I'm going to get rid of some of the highlighting just to make a few points about what we've done here. What does the Biot-Savart law do? Why do we use it? What it tells us is the bit of magnetic field that gets created by a little bit of current carrying wire, a distance r away from that bit of current carrying wire. So it's a very general law, right? It's something that somebody derived mathematically after lots and lots of experiments. And in this problem, we have this little bit of arc of wire, and it's producing this little bit of magnetic field. And what we want to know is, what is that magnetic field at this point P? So that's what the Biot-Savart law is telling us. And we use that, and we integrate it around the loop, and we realize that every loop creates a magnetic field that points upwards through the middle of the loop. And the strength of that magnetic field depends on if you're right at the center, at the plane of the loop, or if you're somewhere else up here at point P. So just backing away from some of that math for a sec, I want to show you guys another right-hand rule. Okay, yet another one. If you're interested in calculating the magnetic field created by a loop, a circular loop of current carrying wire, take the fingers of your right hand and curl them in the direction the current's going around the loop. So in this case, you can see the current flowing around. I guess it's kind of like in a counterclockwise sense if you're looking down at the loop in the page. Curl your fingers around the loop like that, and your thumb points up. And that says that the magnetic field created by that current carrying loop at the center of the loop points up out of the loop. Another way to think about that is like all those bits of current around the loop are combining to create a field that adds up and points upwards out of the loop. And that's a general result for all current carrying loops. Now, think back to what we talked about yesterday with the magnetic dipole moment. Remember, we were using the dipole moment to help us understand the orientation of a loop relative to a magnetic field and the torque that results. And what did we do for that dipole moment? We curled our fingers in the direction of the current as it's going around the loop, and our thumb pointed in the direction of the magnetic dipole moment. And it's no coincidence. Current carrying loops experience a torque due to other magnetic fields that somehow depend on their relative orientation, and the magnetic dipole moment vector, the direction of our thumb, tells us the direction of that dipole moment, and that in turn tells us how the loop rotates, how the torque acts on it. But here, we're not interested in the torque on this loop due to some other magnet. We're interested in the magnetic field created by this loop itself. And the same sense of that magnetic dipole moment applies here. The current in the loop results in a magnetic field that points up out of the plane of the loop. And it's no coincidence your thumb points in the direction of that magnetic dipole moment vector. It's exactly the same thing. And remember yesterday we talked about our simple model of magnetism, the idea that in a simple hydrogen atom, a single proton, a single electron orbiting it, that electron is a moving charge acting like a current, creating a tiny magnetic dipole moment vector for that single hydrogen atom. And more complicated metals like iron, that have lots of outer electrons that are all orbiting in the same way add up to create their own little magnetic dipole moment vectors. That's why iron's magnetic. It's all those little magnetic domains and all their little magnetic dipole moments that are adding up. So we've derived a pretty cool result here that not only describes the magnetic field created by a single loop, it really is the fundamentals of what's happening in a microscopic level in matter that causes magnetism in the first place. Okay, I've run a little bit past the time that I wanted to start for our break. We're gonna take a break now, and we're gonna take a break until 1:30 p.m. So 7-ish minutes. We'll take a break till 1:30, and then we'll get started again. Okay, guys, welcome back. It's 1:30 now. We've got a little bit over an hour until our next break. Our next break will be at 2:40 p.m., just a bit over an hour from now. Before we move on, I just want to highlight a few things on your formula sheet for you. Let's go over to your formula sheet here. And in the second last page, in the section on magnetic forces and fields, we've got the force on a moving point charge due to a known electric and or magnetic field. We've got the force on a current carrying wire of length L or a wire segment, depending on its orientation. That's great. So those are the effects of magnetic fields on things. Now, here is the Biot-Savart law. And again, just to highlight, it's written two ways. You can use whichever way you prefer, but I like the r hat way, just because r hat is a unit vector, so it makes the math a bit easier. And remember the trick that we did in the last problem, dl cross r hat is just dl itself. So that lets you express everything in terms of the geometry of the problem. Now, more generally, what does the Biot-Savart law tell us? Why do we use it? Why do we care, right? Well, maybe we don't care at all, but we need to a little bit for our exam. What is it? It's telling us the bit of magnetic field, dB, created by a little bit of current carrying wire, IDL, a distance r away from that wire. And the reason for this complicated dl cross r hat is to account for the geometry. And that geometry is another right-hand rule that we've used a few times now. Point your thumb in the direction of the current, curl your fingers, and your fingers give you a sense of the bit of magnetic field created by that bit of wire. We've looked at now two special cases of the Biot-Savart law, and really the only ones you need to know. A long straight wire, mu naught I over 2 pi r. That's the magnetic field created a distance r away from the wire. So let's highlight that. And we just derived, as part of a long answer problem, the other form of the Biot-Savart law for a loop of wire. And that's a loop of wire of radius r, big R in this case. Now notice that the formula on your formula sheet also has an n in it. And what is that n? That's the number of loops of wire. So in the last problem we did just before the break, we had a single loop of current carrying wire, and we calculated the field mu naught I over 2 big R created at the center of that loop. If we had n loops of wire, the field would be n times stronger. And this is actually how we make big magnets. You might have heard of electromagnets, and that's how we create them. We get wire and we wrap a bunch of turns around, and the more turns of wire we get, each carrying the same current, well, we magnify the effect by a factor of n. Okay, so those are the two special cases for the Biot-Savart law. And if you have to do a Biot-Savart law calculation on your exam, it's only going to be one of those or the other. We've done both now. I just want to highlight another problem for you, and I'm going to write it here at the bottom of the screen, and you guys can choose to write this or capture it wherever you want. So another Biot-Savart problem to look at, if you want to study this and practice it some more, you'll find on page 231 of the booklet, or that corresponds to page 66 of exam package. There's another problem there involving the Biot-Savart law for a straight wire segment. We've already done one of those yesterday, so I'm not going to spend time here in the session on it, but if you want to practice again, it's there. All right, so I'll just pause there and see if there's any other kind of general questions about the Biot-Savart law, what it is, how we use it. Okay, and just to let you know how I feel about the Biot-Savart law, the only reason that I really understand it and I'm comfortable with it is because I've been teaching this course for so long. I know that when I first encountered the Biot-Savart law in my electricity and magnetism 2 class in second year of my undergrad at Waterloo, I had no idea what the Biot-Savart law was. So I totally feel for you guys if you're kind of confused about what it is. Hopefully the words of explanation we've done help, right? It's a mathematical way of calculating the bit of magnetic field created by a bit of current carrying wire, accounting for all the geometry involved. Where are you interested in calculating the field relative to that bit of current? That's really what the Biot-Savart law is. Now, if you consider how hard it was for those people to derive that law, they knew that there was some interesting right-hand rules involved from all the experiments they were doing. So they knew there must be a vector cross product involved. And you can see there's vector cross products and right-hand rules involved in magnetism all over the place. And really that's kind of the fundamental thing about magnetism, is that everything happens at right angles to other things. So that's why there's so many right-hand rules and so many vector cross products. But they were able to distill down all of that physics into a really concise math equation, which is this IDL cross R hat that helps account for both which direction the current is going and where are you interested in calculating the field relative to that. And that's what's contained inside that cross product in the Biot-Savart law. Okay, so that's enough about Biot-Savart, I think. Practice a few more of those. And as we've seen, right, there's a few problems from previous year's exams where we have to know how to do that calculation. I just want to highlight one last thing about that previous problem, though. And I'll go back to the exam package to do that. So this should be back on page, I think it's 52 of your exam package. This is the problem we just did. And I just want to highlight something. You get 3 out of 8 marks in part A just for stating which direction the magnetic field at P points in. And remember the magnetic dipole moment. For a loop of current carrying wire or a single moving point charge that's traveling in a circle, curl your fingers in the direction of the current and your thumb points in the direction of the magnetic field that that current creates. So this is a special case right-hand rule, and you can get 3 marks on this problem just for knowing that. 3 out of 8 ain't bad. If you're having trouble with the math that goes into the Biot-Savart law and the other 5 marks, I'm pretty sure that you could cobble together at least 2 or 3 more marks from doing some of that math. And as a result, you get, I don't know, at least 5 or 6 marks out of 8 for that. So don't let the Biot-Savart law intimidate you, in other words. Okay, what I want to do now, just before we dive into electromagnetic induction, I just want to highlight something that's in your course booklet for you. So maybe a little bit of a break from physics and a little bit more about how to best tackle your exam. Let's go to the second last page, page 293 of your course booklet. Just a little mental break from all the calculus for a sec here. And just some tips on getting the most marks on your exam. And that previous problem is a really good way of highlighting the strategy here. Just before we dive into this, when I first started teaching for CourseCram many years ago and I developed this course booklet, they asked me to create a section on exam writing tips, like how do you get the most marks on your exam? And as I was writing that, I kind of thought back to my experience in my undergrad and grad school and like, what's kind of the best way to distill all the wisdom that I gained about writing exams? And I thought back to all the exams that I had written over the course of all those years of school and added them all up. And I wrote nearly 150 midterms and exams over the course of my undergrad and graduate degrees. And by the time you write that many exams, you get really good at writing exams and getting part marks. So what I've tried to do in section 9 here is just distill that down into some bits of wisdom. Some of these might seem really obvious to you. You might already do these yourself. Some of these might be something you hadn't thought of and you might find helpful. Section 9.1 here is really generic, and I won't spend any time on it. It's really just about like a problem solving strategy. So we won't spend time on that. I want to spend a bit more time on section 9.2. We know the format of your exam this year. The profs have shared that format. We talked about it in part 1 on Friday evening. We know that the multiple choice portion of the exam is only worth, I think it was 23-ish% of the total marks. So right away, that should give you a sense of how to spend your time when you're at the exam. And what I would suggest that you do before you start answering any questions on your exam, read all the problems and all the multiple choice questions and just take stock of what they're asking you to do before you actually solve anything. Just read them all over and try to categorize them like, oh yeah, this is a magnetic force problem. Oh, this is a circuits problem, whatever. And beyond that, even try to categorize them by difficulty. Like this one's straightforward for me. This one is, I would say, difficult but solvable. This one is really hard. And after you've done that, spend your time in the places that you're comfortable and that you know you can get the most marks. So translating that into a strategy for attacking your exam, work through the easy multiple choice questions first. And if you can't figure out how to solve a multiple choice question in less than about 2 minutes, just give up and move on. It's only worth 1.5 marks out of 60. So it's not worth the time. Don't go through the multiple choice questions in order, and don't try to solve every one before you move on to the next one, okay? You want to spend the majority of your time on the long answer problems, and given the timing involved, that means at least 2.5 hours of the time allocated to you guys. And if you have any time left over at the end, that's when you go back and you take a wild guess on any multiple choice questions you couldn't solve, and you just take a stab at writing something for any of the parts of long answer problems you weren't able to do. And as you get into your upper years, like you guys might already be doing this might seem intuitive to you already for some of you, but as you get into your upper years, you'll start to get better and better at this process of like casing out the exam and figuring out where to spend your time. And you don't have to do the exam in a linear way. You don't have to start at the beginning and keep going in a linear way to the end. You can answer the questions in any order that makes sense for you. All right, just flipping over to page 294, some other tips about maximizing your mark. And again, some of these might be intuitive for some of you, some of these might be helpful. In the course of all the years of school, grad school and undergrad that I did, I learned that my mark was most strongly correlated to how well I slept the night before. In first year, I used to stay up all night trying to learn more physics the night before my exam. And I learned the hard way that if you do that, there's a really good chance you're going to make a mistake on something you already know and are comfortable with. And so you learn to have this really fatalistic approach where you say, it's midnight the night before my exam, and I know X% of APSC 112. Maybe X is 65 or 70%, maybe it's 95% because you came to course cram, whatever it is, but the night before your exam, you know a certain amount of APSC 112. And if you stay up all night trying to learn the other 1 minus X%, chances are you're going to make a mistake on the stuff you know. So just go to bed early and get a good sleep and be fatalistic about it. In fourth year of my undergrad at Waterloo, we had a quantum physics course, and I will truthfully tell you I don't understand anything about that course at the time and even since. And I knew a certain amount of that course before it was time to write the exam, and I went out the night before with my friends and I had some beers and chicken wings. I said, you know what, I know this much about quantum physics and I'm not going to learn any more between now and tomorrow morning. So you learn to get more comfortable with that idea as you go on. All right. I'm just going to highlight a couple other things. We talked about flipping through the whole exam before you start. And we talked about managing your time, starting with the questions you know you can answer easily and spending the most of your time on the difficult but solvable questions. And this one, I just want to highlight one more time. Always write something. So if you have a few minutes at the end, write something, even if it's words. You can often get part marks for writing some words. And a little anecdote about that, in the 4th year of my undergrad at Waterloo, I took a laser physics course. My prof, Donna Strickland, for that course, coincidentally won the Nobel Prize in physics for lasers. So needless to say, that was a really hard course. And I was really good at it. I'm actually a laser physicist now. That's what I do for my job. And I was really good at it. And going into that exam, I was really confident. I knew I was going to get a good mark. And I was solving the 3rd of 3 questions in the 4 hours that we were given. And I was writing Einstein's rate equations for lasers. And I realized that I'm not going to have enough time to finish this derivation. I knew how to do it. I knew how to do all the math. And if I had a few more minutes, I would have been able to finish it. But I looked at the clock and I said, you know what, with the 5 minutes I have left, I know I can't finish this. So instead of writing more math, I just started writing words. And I wrote a paragraph and I said, I can see that I'm running out of time. Here's where I got to with the math, but here's what I would do next if I had more time. I would do this, and then I would do this, and then I would do this, and the final result would look something like this. And I know from my mark that I got a lot of part marks by doing that. So that always writes something. It might seem like really obvious, but it really means something. You can get part marks just by writing some words here and there. And that can help you guys maximize your mark. One last thing that I'm going to highlight is try really hard to write neatly. I know that I'm not guilty. I know that I'm guilty of not always writing the neatest on my tablet here. It's just hard to write really clearly on a tablet. But when you're writing on your sheet for your final exam, it makes the job of your marker, your prof, easier if they can read what you're writing. And you might have noticed when we do long answer problems, we put a little box around our answer to each part, and that's to help your profs mark it, because when profs mark exams, they don't read them linearly. You know what they do? They go to the end of the question and look at your answer, and if it's right, they skim back a little bit and say, did they do all the work? Yeah, it looks like they did, full marks. Or if they didn't get the right answer, but there's a lot of math there, they go back and they try to spend a bit of time to see where you went wrong. That's the way profs spend their time marking exams. And so if you highlight your final answer to each part, it will make it easier for them to mark. And if you write your math a little bit more neatly, it will make it easier for them to give you part marks if they look back through your work. All right, so a little aside from physics, but just some wisdom about writing exams. And hopefully you guys find that helpful. All right, let's get back into physics now. And what we're going to get into now is electromagnetic induction. That's chapter 8 of your booklet. That starts on page 245. And once you find chapter 8, page 245, it should look like this on your screen. Okay, so we've learned some things about magnetism. We've learned about effects of known magnetic fields on objects like current carrying wires, loops, moving charges. We've also learned about causes of magnetic fields, how to calculate the magnetic field created by a current. Now we're going to learn about another manifestation of magnetism. It's called electromagnetic induction and Faraday's law. But in order to understand that, it's critical that we understand something called magnetic flux. And flux is how much of a vector passes through a surface area. Okay, that's all it is. How much of a vector passes through a surface area. And the way we account for that mathematically is with this vector dot product. We define this thing called the flux, the capital letter phi, and the flux of the magnetic field. We use B for magnetic field. So phi subscript B, that's the magnetic flux. And we use this vector dot product to help account for the relative orientation of a vector and a surface area that it can pass through. And just to highlight what I mean, I'm going to show you guys something here. This is a piece of just standard paper. This is what I've written my teaching plan on. Okay, so here's a piece of paper that's blocking me from the camera. And the flux of camera through this surface area is very big, right? You can see lots and lots of that area. But I'm going to take that same paper and I'm going to turn it at 90 degrees to the camera. And now the flux of camera through that cross-sectional area is very small. Not very much of what you can see is passing through that surface area. So that's the notion of flux. It's not just the strength of the magnetic field vector that matters, it's the orientation of the vector and a surface area that's passing through that matters. And we account for that with this dot product. And the dot product of two vectors is the magnitude of one times the magnitude of the other times the cos of the angle between them. And that cos theta is the angle relative to the normal vector through the surface. So that's the notion of magnetic flux. Mathematically, it accounts both for the magnetic field strength, but also the orientation of the magnetic field vector as it passes through a surface. If you have a magnetic field that's not uniform, or if you have a uniform magnetic field and a surface area that's not just purely a rectangle, that's not uniform, well, then we have to integrate the flux passing through each little segment of that surface area. And that's what this picture at the bottom of the page tries to tell us. It says, figure out the little bit of flux passing through the little bit of area, and then add up all those fluxes. And the important thing to note is that flux is a scalar quantity. So we do that dot product, it results in a scalar quantity. And really what we're just doing is adding up that scalar flux through all the bits of surface area. Okay, so that's mathematically what magnetic flux is. And there's some pictures at the top of the next page that illustrate those different extremes of flux, right? Minimum flux and maximum flux. Okay, so what is Faraday's law? Faraday's law is an experimental law. It's something that Thomas Faraday discovered, Michael Faraday discovered experimentally. And the way he discovered it experimentally was in the lab with some current carrying wires on his desk, bringing a magnet nearby. What he noticed is that the reading on a voltmeter from Ohm's law and the current passing through a wire would change depending on how quickly he moved the magnet nearby those wires. If he held the magnet steady and the current in the wire was steady, then there would be a constant voltage reading on his voltmeter. If he moved the magnet somewhere else and waited for a little while, the reading on the voltmeter would be constant. But it was the process of moving the magnet and literally the rate of change of moving the magnet that caused a change in the voltage reading. And so somehow this moving magnet, somehow this time-varying magnetic field was having an effect on this wire, and it was creating what we call this EMF, this Faraday's law. And so when he figured out all the math to this, what he realized is that the EMF, so think of this as a voltage, the voltage created in his circuit was dependent on the rate of change of the magnetic flux, which is the rate of change of the BA cos theta. In other words, if you change the strength of the magnetic field with respect to time, or if you change the cross-sectional area of your circuit exposed to magnetic field with respect to time, or if you change the orientation between the magnetic field and the circuit with respect to time, any of those things can cause a time-varying flux and result in this induced voltage. And you can go one step further from Ohm's law, right? V equals IR. So instead of expressing this induced voltage, we could express an induced current. So this is purely an experimental observation. And he figured out that the induced voltage or current was proportional to the rate of change of the magnetic flux. Okay, there's another wrinkle to all this, and it's called Lenz's law. And Lenz's law says that that induced current in the circuit will flow in such a way that its own magnetic field opposes the changing flux. We're going to go through a whole bunch of examples of Lenz's law to get comfortable with it, but that's what Lenz's law is. We're going to come back to lots of examples of that. And one last thing, you might have noticed this negative sign in Faraday's law. And that negative sign is really just a reminder to do Lenz's law. That's all it is. You don't have to mathematically use that negative sign for anything. It's just a reminder that the polarity of that induced voltage or the direction of that induced current is such that it opposes the changing flux. It minimizes the changing flux. Okay, let's go over to the next page, page 247. So just to summarize everything, you've got some kind of circuit sitting on your lab bench. And that circuit describes some area, some cross-sectional area that could be exposed to a magnetic field from some external magnet. And Faraday's law says that nothing happens unless you change the flux through that area with respect to time. Lenz's law says that the induced current that results flows in a direction to minimize the changing flux. And writing it all out, we wrote this on the previous page, but just highlighting it here in equation form. Faraday's law says that that induced EMF is proportional to the rate of change of flux. There's three ways to change the flux with respect to time. You could either change the magnetic field with respect to time, you could change the orientation of the circuit with respect to the magnetic field with respect to time, or you can change the angle, the orientation, or any combination of those. Okay, so that's what Faraday's law is. And the best way to get comfortable with Faraday's law is to look at some examples of it. Let's go to page 258 now, page 258 in your booklet. And there's some room on page 258 to look at this multiple choice question from page 40 of your exam package. And we want to look at question 16 on page 40. So it's this one down near the bottom, and I'll just highlight it on the screen here, number 16. I'll just give you a moment to read that one over. Okay, as we read this one over, there's three different metal coils, each labeled A, B, or C, and they're heading into a region where there's a uniform magnetic field. They move with the same constant velocity. They all have the same resistance. And as they enter this magnetic field, there will be an induced current in them. If you see the word induced in any question on your exam, right away you know you're dealing with Faraday's law and induction. And the question is, for which of these coils will the current be the greatest as they enter? Now, you guys might have already started thinking about this and answering it yourself. I'm going to give you guys a moment to think about this, and I'm going to launch a poll here just in the Zoom, and you guys can answer that once you're ready. Okay, looks like most people have taken a stab at this one. Oh, still a few questions, still a few answers coming in here. Let's give it another minute. Okay, the vast majority of people have answered, and there's quite an interesting distribution of answers here. I'll just share that up on the screen if you're interested. Notice that the possible answers, right? You could choose one of the three loops, A, B, or C, but then there's tempting other alternatives, right? D, the current is the same in all three cases, or there's no induced current at all. All right, let's work through the math of this and understand what's happening here. I'm going to go back to our course booklet, and we'll just compare what's happening for these three different loops. So we're talking about Faraday's law here, and it is always helpful to write down Faraday's law in equation form. The magnetic flux is B dot A or BA cos theta. And Faraday's law is that the induced EMF, or related to that, the induced current from Ohm's law, is minus d dt of that magnetic flux. And we could go one step further. Now, for these loops, they show us on the question that the magnetic field is out of the page. And that the loops are all moving to the right with the same speed. And so if you consider the angle between the normal to any of those loops and the magnetic field, normal to any of those loops, perpendicular to the plane of any of those loops, is out of the page. So theta equals 0 in this case. So this is just 1. And really, that induced current is going to be related to the rate of change of B times A. The magnetic field itself is constant. And so really, the induced current is going to depend on the rate of change of A, which is the area of a given loop that's exposed to that uniform magnetic field. Just going to annotate that on here. And just to take that one step further, if we consider, let's say, an XY coordinate system on our screen, B over R times the rate of change of the area of the loop, we could express that as, I guess, like X times Y, right? Width times height of loop. And if you consider that for a given loop, that Y is constant, then the induced current really depends on the speed of the loop and the height of the loop. that speed is the same for all loops. And so really it's the height that matters. And you can see that loop C is higher than the other ones. And so it would have the biggest induced current. So this is a good little problem just to get ourselves acquainted with Faraday's law and rate of change of flux. That's really what matters. And there's a really good question that came in on the Q&A. How is the area of the loop changing? The area of each loop is not changing, right? The area of each loop, like width times height, is constant. But the portion of that area that's exposed to magnetic field is changing. There's a period of time when no part of any of those loops has entered the field region. And during that period of time, the flux through any of those loops is zero. Later on, there's a period of time when all the loops have fully entered that field region. And while all those loops are in the field region, it doesn't matter how they move around. The flux through any of those loops is also constant with respect to time. The rate of change of that flux is zero, and there's no induced current. It's only as the loop is crossing into that magnetic field region that the portion of loop exposed to field is changing with respect to time. And it's really that time-dependent nature that matters for Faraday's law. And so the reason I wanted to do this question, for some of you guys, this might have been really straightforward. For some of you, maybe not so much. And the reason I wanted to do this one is it really highlights, for Faraday's law questions, start by writing that equation for the flux through the loop. Remind yourself that it's the rate of change of flux that matters. And then ask yourself, what part of that flux is changing? In this problem, the magnetic field was constant with respect to time, but it was the area of the loop exposed to magnetic field that was changing with respect to time. All right, so that's a good little kind of warm-up question on Faraday's law and flux. Let's go to page 252 now. We'll look at another problem on page 252. And once you get to page 252, there's some room to look at the multiple choice question 19 from page 20. Once you get to page 20, it's question 19. So partway down that page, and I've highlighted it at the top of the screen here. And I'll give you a moment to read that one over and consider your answer. And I'm going to go ahead and launch that same polling question again. And when you're ready, you can enter your answer. Okay, it looks like the majority of people have entered their answers here. I'll share the results for us. So the question here is, we've got this rectangular conducting loop. It's moving with a constant velocity into this region where there's a uniform magnetic field out of the page. We see the word induced here, so right away we should be thinking about Faraday's law, induction, and so on. And the question is, which direction would an induced current flow? And the correct answer here is A, clockwise. And I'll walk you guys through why that is. And by the way, it's no surprise to me that there's kind of a almost equal distribution of answers here, clockwise and counterclockwise. But let's walk through this. In order to figure this out, we need to use Lenz's law. And Lenz's law is a result of Faraday's law. So let's just write the whole thing again to make sure that we're comfortable with this. This is just really good practice. The definition of magnetic flux, B dot A or BA cos theta. And in fact, I'm just going to reword this a little bit. Sorry, guys. Let's just start from the beginning. This is the definition of magnetic flux. This is Faraday's law. That the induced EMF, or from Ohm's law, the induced current, is related to the rate of change of that magnetic flux. So really it's related to the rate of change of something related to BA cos theta, the strength of the field, the cross-sectional area exposed to that field, or the orientation of the loop. And this little negative sign here is a reminder to use Lenz's law. And Lenz's law is what we use to figure out the direction of that current. So what have we got here? We've got a loop. It's moving at a certain speed, and it's entering a region where there's a magnetic field out of the page. And let's say there's some boundary where that loop starts to enter that field region, and the flux through the loop starts to change. So to use Lenz's law, you have to ask yourself, is the flux increasing or decreasing with respect to time? But not only that, you have to relate that to the direction of the background magnetic field. Let's walk through that. As the loop starts to enter that field region, there's a magnetic field vector out of the page towards you. And as the loop starts to enter that field region, the portion of that loop exposed to that outwards magnetic field is increasing with respect to time. As time goes on, more and more of that cross-sectional area of the loop is exposed to that outwards magnetic field. So the magnetic flux is out of the page and it's increasing with respect to time. In this case, the magnetic flux is out of the page and it's increasing with respect to time. And Lenz's law says that the induced current in the loop will create its own magnetic field to oppose that change. Currents create magnetic fields, and if we wanted to oppose an increasing flux out of the page towards you, you need to have an induced current that sets up its own magnetic field into the page. Taking your right hand and curling your fingers such that you get an induced field into the page means that you need a clockwise current to achieve that. That induced magnetic field, curling your fingers in the direction of that induced current, that induced magnetic field would be into the page. And I'm just going to put little subscripts here. There's an induced current as a result of that changing flux, and the magnetic field created by that induced current opposes the external magnetic field. Now, Lenz's law is actually a statement of conservation of energy. It might seem kind of weird, but what Lenz's law is saying is that current will flow in whatever direction opposes that changing flux. Magnetic flux is not a vector, right? Like mathematically, if we look up near the top of the screen, magnetic flux is a scalar quantity, but it's really helpful to think of it as a vector. That external magnetic field, B, that points out of the page, imagine a vector that's pointing out of the page towards you that's getting longer and longer with respect to time. That's another way for the flux out of the page to be increasing with respect to time. So imagine a vector pointing in the direction of that external magnetic field, B, out of the page, but getting longer and longer with respect to time. To oppose that, point your thumb in the opposite direction. Your fingers curl in the direction of the induced current required to create that opposing magnetic field. And that tells you what direction it has to point in. And in this case, that would be an induced field into the page and correspondingly a clockwise induced current. I'm just going to pause there and see if there's any questions on that one. Yeah, so there's a question, well, how do you know that you want the current, the induced current's magnetic field to oppose the original magnetic field? The reason you know that is Lenz's law. And Lenz's law is a statement of conservation of energy. One way to think about that is that the loop doesn't like changes in the magnetic field it's experiencing, and it creates its own current to oppose that. So walking through it one more time, in this case, the flux due to the external magnetic field is out of the page and it's increasing with respect to time. Imagining a vector pointing out of the page, getting longer and longer with respect to time, and to oppose that, your thumb of your right hand should point the other way, into the page in this case. And in order to achieve a field into the page, the induced current would have to be clockwise. So that's the trick that I use for Lenz's law. Just pausing for a second, with Lenz's law, consider that there's only 4 possibilities, right? The flux can be into the page or out of the page. The flux can be increasing with respect to time or decreasing with respect to time. You could walk through those 4 possibilities with your right-hand rule and make a little truth table that says what direction is the induced current corresponding to each of those possible changes in flux, in or out of the page, increasing or decreasing. All right. There's a question here. Can I just use my left hand for this kind of problem? Maybe. I don't know. I've never thought of that. If you convince yourself that your left-hand rule works, then go for it. I'm not really sure how that would work, but I'll let you figure that one out. And if you convince yourself that it always gives you the right answer, that's great. You can go for it. Yeah, there's a couple questions. Just how do we know that the flux is increasing again? So let's just walk through that one more time, because there's a lot happening with flux, Faraday's law, and Lenz's law. Just starting at the top of the screen here, the definition of flux is the area exposed to magnetic field multiplied by the magnetic field strength, accounting for the angle between them. Faraday's law says the induced EMF, or the induced current, is proportional to the rate of change of that flux. And notice that there's 3 different ways for the flux to change with respect to time. Either the magnetic field strength can change with respect to time, or the area of loop exposed to that magnetic field can change with respect to time, or the orientation between the loop and the field can change with respect to time. And in this particular problem, the magnetic field itself is constant, the orientation of the loop with respect to the field is constant, and really, it was the area of loop exposed to the field that's changing with respect to time. The magnetic field from whatever external source they tell us is pointing out of the page. And as the loop enters that field region, more and more of the cross-sectional area of the loop is being exposed to that field with respect to time. So in this case, the flux through the loop is out of the page and it's increasing with respect to time. To oppose that, the loop creates its own current and its own magnetic field that results in its own field pointing into the page, and to create that, it needs a clockwise induced current. So that's Lenz's law. You need to practice a whole bunch of those to get really comfortable with Lenz's law. What you'll find, we looked at 2 multiple choice questions here about Faraday's law, induction, and Lenz's law. What you'll find is that variations of those 2 questions show up every year on the final exam. So when you go back through and you're looking through the rest of the problems in the exam package, you'll see those patterns, you'll see those problems, just practice them a few times. And once you get Lenz's law, like once it clicks, you've got it. The important thing is to ask yourself, is the flux increasing or decreasing, and in what direction? That's the crux of Lenz's law questions. All right, in your booklet, let's go back and review another effect of magnetic induction. We're going to go to page 248 now. Page 248 and section 8.5. And this is another type of problem called motional EMF. Not emotional, but this type of problem can make you very emotional. Let's consider what's happening in this interesting scenario. Let's say that we create a magnetic field that's pointing into the page. So however we do that, let's say we get a big horseshoe magnet and we point it such that we've created a magnetic field into the page. And let's say that we get some kind of a conducting bar. This is a conducting object. And we move it through that magnetic field at a constant speed, at a speed v. So consider what happens at a microscopic level to electrons in the bar. Consider one electron in the bar. That electron is moving through a magnetic field, so it experiences a force. Remember QV cross B, the force on a point charge moving through a magnetic field. So let's do the right-hand rule here. We've got an electron moving from left to right through a magnetic field that's pointing into the page. Let's point our fingers to the right, curl your fingers into the page, and you would get a magnetic force on a positive point charge pointing up on that positive point charge, but this is an electron, so flip your hand over. Electrons feel a magnetic force downwards. And that's what this is, FB or FM, we could use that symbol for the magnetic force. So what happens as this bar moves through this magnetic field? Electrons start to gather at the bottom of the bar. And as electrons gather at the bottom of the bar, they leave behind the absence of electrons at the top of the bar. And if we separate charges like that, we create electric fields. The electric field points from positive charge to negative charge. So there's an electric potential that's created across this bar, an induced electric field that points this way, downwards. Electrons accelerate opposite to the electric field. And so that electron would experience an upwards force due to that electric field. There's some kind of balance that has to get struck here. There's an equilibrium condition that's reached. And at the equilibrium condition, the magnitude of the electric force pushing electrons up and the magnetic force pushing electrons down balances out. So this says that the magnitude of that electric force is equal to the magnitude of that magnetic force. And in order for those things to balance out, we can get a relationship between the electric and magnetic field strengths. And this equation is just like the velocity selector equation we saw earlier. We've seen this a few times now. We saw it with velocity selectors, we saw it with the Hall effect, and now we're seeing it here with motional EMF. The notion that when you move conductors through a mixed electric and magnetic fields, there's some relationship between those quantities. And if you want to relate the electric field to the induced voltage across the bar, remember voltage is electric field times distance, then you can get an expression for the EMF, what we call the motional EMF, induced on that bar. BLV. L is the length of the bar, and V is the speed of the bar. We've seen this equation before, right? We saw this a couple questions ago when we were looking at those loops passing into the magnetic field. Remember, we derived an expression for the induced current in those different loops, A, B, and C, right? And we found this equation, BLV. It's the same thing. It's exactly the same effect. It relates the induced EMF or the induced current due to the motion of a conductor through a magnetic field. And we'll go over to page 249 and see how this manifests as a problem on exams. And there's problems like this almost every year on the exam. If you get this conducting bar and you attach it to some conducting rails that have a resistance, and you pull the bar at constant speed through that magnetic field, an induced current will flow. And from Ohm's law, you can calculate the relationship between that induced EMF and the V equals IR of Ohm's law. And there's something interesting to consider here. This is just taking it one step further. As you move this bar with constant speed, and as an induced current flows through it, there must be a force acting on the bar because it's carrying a current and it's in a magnetic field. And that force opposes the motion. If you want, you could call this a resistive magnetic force. And this is true anytime you move a conductor through a magnetic field at a certain speed. It's always going to generate an induced current. And as a result, there's always going to be a resistive magnetic force that acts, that opposes the motion. And this, again, is a statement of conservation of energy. Nature doesn't like the fact that we're changing things on it. Everything was in equilibrium before. Why did you do this? And so as a result of the motion of the bar inducing a current and the resulting force opposing that motion, what we find is that to keep the bar moving at a constant speed, we have to apply a constant force. And you can take this even one step further. And if you look at power, remember from APSC 111, we had a notion of mechanical power, which was the applied force times the speed that something is moving at. And when we talked about circuits, we had a notion of electrical power. This is a statement of conservation of energy. You have to do a certain amount of work per unit time to keep the bar moving at constant speed. That same amount of energy gets dissipated as heat in the resistors in that circuit as electrical power. And this, if you want, you could consider this as magnetic energy conservation. And now you see why we call this emotional EMF, right? Because it combines all these things together in one problem. But once you've studied this once, like we have today, And once you learn to recognize, if you have a moving conductor and a resistive circuit in a magnetic field, there's going to be an opposing magnetic force. Once you recognize that situation, you can actually solve these really straightforwardly. We're going to take a look at an example of that. Let's go to page 253. Page 253. And there's some room there to look at the long answer question on page 20. Pardon me, the multiple choice question on page 20. Multiple choice question 20 on page 20. And it's just down at the bottom of the screen. We were just looking at question 19 earlier. Whoops. Now we want to look at question 20. Guys, hang on, sorry. I think I might have a typo in my teaching plan here. Just bear with me for a sec, because this isn't actually the question I was thinking of doing. Sorry, guys. Just give me 1 sec here. I'm just going to track down the actual question that I wanted to do. Bear with me for 1 sec. Okay, sorry, guys. I just have the wrong thing written in my teaching plan. This is not the one I wanted to do right now. Sorry about that. We're going to go to page 86 in your exam package. Let's go to page 86. And I want to do question 8 on page 86 in your exam package. And this one, if you want, is on, there's some room for this on page 260. We're going to come back to that when we write our solution. Sorry for that confusion, just misreading my teaching plan here. Question 8 on page 86. Okay, I'm going to launch our little poll question here again so that you guys can enter your answers. And as you work through this one, consider that this is what we call the motional EMF, a conductor that's moving through a magnetic field, and calculating the induced EMF or the induced current in that conductor. Okay, just keeping an eye on the clock here. We'll wrap it up in a few seconds. It looks like the majority of people have answered this one. The correct answer here is D. There's a 1.29 volt EMF induced with point B, the right edge of the bar, at a higher potential. And let's walk through why that is. So first of all, how do we get started on this thing? We've got a conducting rod, and that conducting rod is moving in a magnetic field with a given magnitude at a constant speed. Right away, when you see that situation, we need to think about motional EMF. And let's go back to our booklet. And as I said, there's some room on page 260 for this one to write your answer. And I'm just going to take a moment and redraw what's happening. We've got a magnetic field into the page. We've got a conducting bar. And that bar has a certain length. It's moving at a speed of v downwards. And when we consider motional EMF, we could just skip right to the equation. BLV. And we know what all those quantities are. We could calculate the magnitude of that induced EMF. The magnetic field is given to us 0.55 Tesla. The length of the bar, 45 centimeters. And the speed of the bar, 5.2 meters per second. And when we calculate that out, we get a 1.29 volt EMF that gets generated. Now the question is, what's the polarity or the sense of that EMF? Which side of the bar, point A or point B, is at a higher polarity? There's a couple ways you could figure this out. One way is to use Lenz's law and the right-hand rule to figure out the direction of the induced current. Another way to do that is to consider what's happening with a single electron in the bar. And one way to think about that is that what would be the direction of the force on a single electron in the bar just due to the fact that it's moving through a magnetic field? So to capture that, I'm going to write it like this. To find the polarity of that EMF, consider the force on an electron. For an electron in the bar. And if you do that, you can use your right-hand rule and figure out the direction that the magnetic force would act on that electron. That electron is moving down in the plane of our page, and there's a magnetic field into the page. And that would result in a force on a positive point charge towards the rightmost end of the bar, towards point B. But this is an electron, so the force is in the opposite direction. And you could label that if you want on your diagram. There's a magnetic force on electrons pushing them to the left edge of the bar. And that results in negative charges collecting at the left end and positive charges collecting at the right end. And that means point B, the right end of the bar, is at a higher polarity. Or a higher potential, I guess, is another way of saying that. I'll just pause there and see if there's questions about that. Yeah, so there's a question about the right-hand rule here. So what we want to do is figure out, we've calculated the magnitude of the EMF induced across that bar. What we want to do is figure out the sense of it, the polarity of it. And the easiest way to do that, I think, is to figure out which direction electrons get pushed in the bar. So consider that electrons are free to move around in that conductor. The electrons are falling downwards with the bar. So pointing your fingers of your right hand in the direction of the velocity vector, V, curl your fingers into the direction of B, which is into the page, and that results in a force to the right on a positive point charge, a force to the left on electrons. Electrons get pushed to the left end of the bar, and they leave behind an absence of electrons at the right end of the bar. And right away, in a way, you could think of that as a battery, right? What we're left with is a battery with that EMF in the bar. You could also figure that out from Faraday's law of induction if you really wanted to. It's multiple right-hand rules and it's more difficult to figure it out and get it right. Practice that if you want on your own time. But I find with these motional EMF questions, the easiest way to figure out the sense or the polarity of that induced EMF is to do that thought experiment about the direction of the force on an electron. And that tells you where the charges go. All right, so that's motional EMF. A little bit later in the last part of our session, we're going to do a long answer problem involving motional EMF, and we'll walk through that. But every year on the exam, there's a question something like this one, where we have to look at a moving conductor in a magnetic field. And the way to solve those is to remember this formula, and we've seen it a few times now, for the EMF induced due to the fact that a conductor is moving through a magnetic field. All right, I'll just pause and see if there's any more questions on that one. Yeah, there's a couple of questions about the sense of the potential, and these are good questions. So let's talk through these. A few people have asked that. Okay, so I think you guys agree with the fact that electrons get pushed to the left end of the bar, point A, and they leave behind an absence of electrons or a net positive charge at point B. So which side is at a higher potential? I'm just going to draw that in a slightly different way. Here's our bar. Whoop. Sorry, not sure what happened there. Here's our bar. And we've agreed that there's a net positive charge at one end of the bar and a net negative charge at the other end of the bar. This is point A and point B. And there's a few ways you could convince yourself that the potential is higher at point B. Here's one way to consider it. That looks a little bit like an electric dipole with a positive point charge at point B and a negative point charge at point A. And that results in an electric field that points like this. The electric field vector points in the direction of decreasing potential. That's one way to look at that. Another way to look at that is from our notion of electric potential and batteries. And in a battery, when conventional current goes like this, it loses potential, right? So that's another way to look at it. There's a few ways to convince yourself that if there's a net positive charge at point B and a net negative charge at point A, then B is at a higher potential. All right. So we're going to pause there. And right now it's time to do our evaluations for the course. And our moderator is going to send a chat in the Zoom chat. So if you look at the toolbar in your Zoom window, you'll see a chat appear, and in that chat, you'll see a link to a Google form that you can fill out. And there's a section in that Google form where you can relate CourseCram for their overall service. You can rate me as an instructor. You can leave your comments about any part of your experience with CourseCram. I get to see all your comments, and those are all really helpful to me. So take a moment and follow that Google form link and fill out your evaluations. Once you finish your evaluations, we're going to take a 10-minute break. We're going to get started at 3:00 p.m. And with our last hour, we're going to do some more long answer problems on electromagnetic induction. All right, guys, so I'll see you in 10 minutes.
the changing world order.
Okay, guys, welcome back. It's 3 o'clock. We've got 1 hour to go here, and we're in the home stretch. We've been working our way through a review of Faraday's law, electromagnetic induction, Lenz's law, induced EMFs, and so on. I just want to highlight something for you. Let's go to your formula sheet, and it should be the second last page of your exam package. And I'm just going to erase a whole bunch of this annotation that I've made on my version here, just so I can highlight something else for you. Just bear with me as I get rid of this. All right. What I want to highlight is Faraday's law and induction on your formula sheet. So at the very bottom of the second last page of your formula sheet, there's a formula here for the magnetic flux. And just remember the other form of that, right? The dot product of two vectors is the magnitude of one times the other times the cos of the angle between those vectors. And in all the problems we've done so far, we've literally written that equation in that form, just to remind ourselves that when we want to take the time derivative of that flux, there's a few ways for the flux to possibly change with time. The other thing I want to point out about Faraday's law is that it's for the induced EMF, so induced voltage. But from Ohm's law, that's equal to IR. If you know the resistance in the circuit, you can calculate the corresponding induced current. The other thing I want to point out is this negative sign in Faraday's law. And this is really a reminder to use Lenz's law. You don't have to carry that negative sign around in your math. It doesn't really mean anything. It doesn't change your answer. It's just a reminder that Lenz's law applies, and Lenz's law can be used to figure out the direction of the induced current that's necessary to oppose the change in flux. And in turn, that will influence the polarity or the sense of the induced EMF. And we saw a problem just now, just before the break, where we looked at that. And the last thing I want to point out about this is there's an N in Faraday's law, and that is simply that if you have multiple loops of wire instead of one loop of wire, then that effect gets multiplied by a factor of N. Okay, so that's Faraday's law and the notion of rate of change of flux. There's one last thing we need to review related to that concept. We're going to go back to page 250 now in your booklet. So page 250, 250. Once you find it, it's section 8.6 on generators and motors. And electric generators and motors work on the principle of induction. And the idea is literally that we get a magnet, we wrap a coil of wire around it, we pass a current through it, and we can cause a force or a torque or a motion to occur. And if we attach that whole assembly to an axle, then it will rotate at a certain rate. And omega, which we use as the angular speed, is in there. And if you wrap n turns of wire, or number of loops of wire, I guess, then you magnify this effect. And if that's an expression for the flux as a function of time, and the induced EMF or the induced current is related to the rate of change of that flux, the time derivative of a cos omega t is an omega sine omega t. And so this formula here is not on your formula sheet. It's very easy to remember or to derive if you want. Consider that you could have a loop or a number of loops that the orientation of that loop is changing at a constant rate. So rate of change of theta is omega, right? So that's one way to look at it or to derive it. You could just memorize that formula that I've highlighted, and I think you can validly use that on your exam without deriving it from first principles. I know they say that you have to derive any formula, but you could just say from Faraday's law and the rate of rotation omega, here is the rate of change of flux through that rotating loop, and here's the corresponding induced EMF. And this is the principle behind electric motors and generators, and the idea that in a motor, you pass a current through the wire, and it results in a torque and causes a motion. In a generator, it's actually the opposite. In a generator, you create a torque, you cause this thing to rotate. You could do that lots of different ways. You could do it with a motor, you could do it with falling water hitting some kind of a turbine, but you cause a mechanical torque, and as a result, that generates an induced current in the circuit. So this is like the motor or the generator equation. And the thing to point out, if this is a sinusoidal function of time, then there's a certain maximum value of the voltage. Sorry, I wanted to do that in a different color, one sec. There's a certain maximum voltage, or also known as the peak voltage. And some variation of this type of thing shows up in the multiple choice questions quite often. Let's take a look at an example. We're going to go to page 259 now. And there's some room on page 259 for the question on page 56. And the question I wanted to do is multiple choice question 7, down at the bottom of page 56. So So it should, whoops, should look like this once you find it. And I'll just give you guys a moment to read that one over. There's so many different things that kind of come together in magnetism problems that you really have to look at the wording in questions to help you figure out what scenario, what manifestation of magnetism we're talking about. Okay, so we're given a uniform magnetic field. We're told that there's a square with certain dimensions that gets rotated with a frequency. And there's a question about the induced EMF in this coil. And they actually tell us in the question that the induced EMF in this coil varies sinusoidally with respect to time according to this equation. And the question is, what is this V naught? So from the information that we're given in that question, somehow we have to calculate this V naught. And the question is, what is this equation and where did it come from? And this is the quote unquote motor equation. Let's go back to page 259 in your booklet and we can write out our solution to this. And so on page 259, let's just write down the formulas that we've got from your formula sheet. Magnetic flux is B dot A, which is BA cos theta. Faraday's law for the induced EMF or the induced current is minus N d phi dt. This loop that we're being talked about is rotating at f equals 40 hertz. So the angular speed of this loop is 2 pi f. And if we wanted to write an expression for Faraday's law, ignore the negative sign. That's a reminder about Lenz's law. We're told that there's only one loop here, so n equals 1. And from Faraday's law, d dt of BA cos omega t, what is that? And just getting this one step further, omega is 2 pi f. And we can compare that to the equation that's given in the question. And the equation that's given in the question is for a voltage, an EMF, same thing, V naught sine 2 pi ft. So by inspection, right away, when you run into a motor question, that peak voltage is BA omega. Or it's BA times 2 pi f, if you want. And we know what all those quantities are. So V naught is the strength of the magnetic field, 5 millitesla. The cross-sectional area of the loop, this one's a square loop of side length 10 centimeters, 0.1 squared, times 2 pi f 40 hertz, and we can calculate the peak voltage, 1.3 times 10 to the negative 2 volts. So the correct answer here is D. Okay, so that's the motor equation or the generator equation and how we use it. And again, noting that it's not on your formula sheet, we can see that it's straightforward to derive or even memorize if you really want to. And it's just from the fact that you have a square loop that's rotating at omega equals 2 pi f. So when you do Faraday's law, you're taking the time rate of change of a cos omega t function. And the peak voltage is BA omega. This whole thing would be multiplied by a factor of n if there were n loops instead of one loop. In this question, n equals 1. So just watch out for questions where they tell you that there's 100 loops or whatever it is. If n is more than 1, just multiply by n. All right, I'll just pause there and see if there's any questions about that. Yeah, there's a question, how do you know to put this omega t instead of theta? It's a fair question. One way to think about it, remember back to the beginning of this chapter when we talked about the definition of flux and that notion of the orientation of a surface with respect to a fixed vector like a magnetic field? So consider the fact that if the loop is rotating, then the flux already is changing with respect to time. It's changing with respect to that omega t function. So that's one way to look at it. I'm really bad at drawing motors, but if you look in your textbook or even online, like at Wikipedia, you can see where that omega t comes from consideration of the fact that the loop is rotating with respect to time. Okay, so that's the motor or the generator equation and how to use it and how to identify those types of questions from your exam. All right, I want to do, with the rest of our time here, a few long answer problems. So the first one that I want to do, let's go to page 265 of your booklet. And there's some room on page 265 to look at this long answer problem from page 3 of your exam package. Page 265 and page 3. And once you find this long answer problem on page 3, it looks like this one. I'm going to give you guys a moment to read this one over and we'll go through it together. Okay, so reading this one over, we've got a conducting rectangular loop with given dimensions, width W, length L. It's got a mass that's noted and a resistance. It's hung in a horizontal magnetic field directed into the page. And that horizontal magnetic field only exists above this line AA. The loop is dropped and it accelerates until it reaches a terminal velocity. And if we read through the parts of the question, we want to get an expression for the current that flows as the loop falls as a function of its velocity. We want to identify whether this current is clockwise or counterclockwise. Calculate how much charge has flowed after the loop has fallen a certain distance, and then find an expression for that terminal velocity. So before we dive into any math, first things first, just to point out, this question comes from the 2006 final exam. That's a long time ago, if you think about what you were doing in 2006. But I do this question every year because it's a really good one to study from, and I've seen variations on this question ever since. So this one, if we can work our way through this one, we'll have a really solid understanding of Faraday's law and induction. Let's think about what's happening. There's a magnetic field only above line AA. There's no magnetic field below that line. There's a conducting loop. It's just a rectangular loop of wire. That's it. There's no batteries or anything connected to it. It's just a loop of wire. Now consider a couple of limiting cases. Consider the case where that loop is entirely below the line AA and you drop it. What happens? It just falls, like it's a mass that's falling due to gravity. And so it would accelerate. If that loop is entirely above line AA and you drop it, now you've got a conducting loop in a magnetic field. And the question is, does it accelerate? Does it reach a terminal velocity? What happens? As long as that loop is entirely above that line AA, it will fall according to gravity. And it will accelerate. But consider what's happening as it's crossing the line AA. And look at the diagram they give us in the question. It's very suggestively showing that part of the loop has crossed below that line, that boundary of the field region, so that only part of the loop is exposed to that field. There's a certain subset, a certain portion of that loop exposed to that field, and that portion or that area exposed to the loop is changing with respect to time. The flux through the loop is variable. It's changing with respect to time. As a result, there's going to be an induced current, an induced EMF. And if there's an induced EMF and an induced current, we know from this notion of motional EMF, when we take a conducting bar and move it through a magnetic field, there's going to be a resistive magnetic force. And we'll derive this and calculate it and figure out why it exists and why it points in that direction. But that's the reason that the loop reaches a terminal speed. Let's dive into the math behind this. And again, on page 265, I should say, page 265, we've got some room to look at this. And I'm just going to start with a quick drawing of the situation. So here's that magic line AA, and here's our loop that has just started falling below that line. And we're told that there's a magnetic field into the page, and that this loop is falling at some speed. Now that speed itself might be a function of time because we have this hint that there's a terminal velocity that's reached. And the loop has a width W, and it has a certain length or height, I guess. So let's try to understand why there's an induced current and why there's a terminal velocity. The flux through the portion of the area of the loop that's exposed to field is B dot A, or BA cos theta. Faraday's law says that there's going to be an induced EMF or an induced current according to minus N d phi dt. There's only one loop here, and we can ignore the negative sign. That's just a reminder about Lenz's law. So really what we're interested in is the rate of change of the flux BA cos theta, the portion of the loop that's exposed to that magnetic field. some of these things are constants and some of them are variables. Cos theta, theta is the angle between the normal vector perpendicular to the plane of the loop and the magnetic field, and that's 0 degrees, right? In other words, the plane of the loop is perpendicular to the field. The magnetic field strength itself is constant. And the width times the height of this loop is the area. And we could come up with a notation for the height of the loop, but I guess we could consider that a portion of this loop is exposed to the field, and that height of loop exposed to the field is varying with respect to time. And so we've got an expression for the EMF induced, or likewise the current that's induced, as a function of time. And what's the rate of change of y as a function of t? That's the speed that the loop is falling. And we've seen this pattern a few times now. This is the equation for motional EMF. It's the equation for one of those slide wire on a circuit things that we've looked at before. This BWV shows up a lot when we're talking about loops sliding into field regions. So there's an expression for the induced EMF or the induced current as a function of time. And so we can rearrange that and get our expression for the induced current, which is what we're asked for in the first part. So B W over R times the speed as a function of time. I'll just pause there and see if there's any questions on that part. Okay, so we've got our answer to part A, which is an expression for the current as a function of time as this loop falls. In part B, the question is that current clockwise or counterclockwise? And to answer that, we have to look at Lenz's law. So looking up at the picture in the top right, we've got an external magnetic flux into the page, and as the loop falls, the portion of loop exposed to that field is decreasing with respect to the time. So flux is into the page and decreasing with respect to time. Imagine a vector pointing into the page, but getting shorter and shorter with respect to time. To oppose that, the induced current needs to create its own field that's also into the page. And that results in a clockwise current. And I'll label that on the diagram here. And if you want, you could call that B induced as a result of the induced current. I'll just pause there and see if there's any questions about that Lenz's law. All good? Okay, now let's take a look at part C. Part C is interesting. It's asking us to calculate how much charge has flowed after a certain amount of time. Sorry, I'll just note our answer for part B. So we want to calculate charge as a function of time. What's the relationship between charge and current? Remember, current is rate of flow of charge, how much charge passes a certain point in a certain time. So another way of looking at that is charge is current multiplied by time if the current is uniform with respect to time. If the current's not uniform with respect to time, then the charge after a certain amount of time is the integral of that current with respect to time. We'll just pause there and see if there's a question. Yeah, there's a couple of unrelated questions here. So it's related to the Lenz's law. And how did we know that the induced current is clockwise, or likewise that the induced field is into the page? I'm just going to go over Lenz's law one more time.
Welcome to your
Okay. So the external magnetic field, the one that's given in the question, the blue vector on the page, is into the page. So there's an external magnetic field into the page, and the flux through the area of the loop is into the page, but it's decreasing with respect to time. As the loop falls farther and farther, less and less area of the loop is exposed to that field.
Okay, good evening,
so the flux is into the page, but decreasing with respect to time.
My name is Will, and I'll be your instructor for this prep session.
The loop induces its own current.
Before we dive into physics, the first thing I want to do is congratulate you guys. As far as I know, today was the last day of classes for you guys for this term. Okay, good evening, everyone. First year, welcome to you.
So getting shorter and shorter with respect to time, and to oppose that change, the loop's own magnetic field also has to point into the page. And from the right-hand rule, that's a clockwise induced current. All right, just back to the very bottom here in part C. It looks like there's no questions about this notion about relating current and charge, so that's good. The important thing is that our expression from part A tells us that the current is not uniform with respect to time. It's a time-varying function because the velocity itself is varying as a function of time. So we can calculate how much current has flowed after a certain amount of time by integrating this expression. And so if we want, we could write an expression for the current that has flowed after a certain amount of time. Let's call it T star, for lack of a better term. That's the integral of our expression from part A, B W over R times V at T dt, and that's integrated from T equals 0 to T star, and there's nothing magical about this T star. What is it? That's the time after which the loop has fallen a height of h. So really what we want to do is just integrate how much charge flows in the amount of time it takes the loop to fall, that height h that they're asking us about. I'm just going to flip over to my next page, and I'll rewrite that so that it's up on the screen for our reference. Some of those things are constants and some of those are variables. B, W, and R are all constants. What do you get when you integrate velocity? You get the total distance traveled, right? So what is this integral? If you integrate the velocity as a function of time over the amount of time that it takes to travel a distance h, you get h. So we've got a nice little expression for the charge that's flowed after the loop has fallen a height of h. I'll just pause there and see if there's any questions. All good? Okay, so we've calculated the amount of charge that's flowed after the loop has fallen a height of h. And finally, in part D, what we want to do is get an expression for the terminal speed. And first, it's worth asking the question, why does the loop reach a terminal speed? So recall that this loop, as it's falling, it's passing through this line AA, and it's falling with a speed that depends on time. And as it's falling, there's a current flowing. And we realized that it was a clockwise current that's flowing. And we know that there's a background magnetic field, and that magnetic field exerts a force on this loop as it's falling. Let's consider the forces, the magnetic forces, exerted on each part of the loop. And so just as a reminder, recall that F equals IL cross B. That's the force on a current carrying wire in a magnetic field. Consider each segment of the loop separately. So consider the leftmost upward segment. There's current flowing upwards in that segment. Point your fingers upwards, curl them into the page in the direction of the magnetic field, and you get a force to the left on that segment. And do a similar thing for the vertical segment on the right. Current is flowing down that segment on the right. Point your fingers down, curl them into the page, and you get a force pointing to the left on that segment. And finally, do it for the segment on the top, the horizontal segment. Current's flowing left to right. Point your fingers left to right, curl them into the page, and you get an upwards magnetic force on that segment. And that is what we've started to call the opposing or the resistive magnetic force. And this is true for any motion of a conductor through a magnetic field. There's always a magnetic force that develops that opposes that motion. That's related to Lenz's law, and it's really a result of conservation of energy. So the forces on the left and right segments cancel out. They're equal and opposite. There's a net upwards force, a magnetic upwards force. And the whole time that's happening, gravity is acting, accelerating this loop downwards. So if we look at all the sum of all the forces in the vertical direction, you could choose up or down to be positive. It's totally up to you. But at equilibrium, in other words, at the terminal velocity, the magnitude of the downward force due to gravity is equal to the magnitude of the upwards magnetic force. And that upwards magnetic force is ILB, so I times the width of the loop times the magnetic field. And we've got an expression for the current as a function of time. So let's plug that in. And here we've just denoted that at the instant that the speed reaches its terminal speed, the speed that appears in our equation in part A for the current as a function of time or as a function of velocity, that's equal to the terminal speed. And we can rearrange that and get an expression for the terminal speed. So just one more step to rearrange and solve for the terminal speed. A few things are going to cancel, and we're going to end up with an mgr divided by w squared b squared. So there's an expression for the terminal speed of this loop as it's crossing that line. I'll just pause there and see if there's any questions. Yeah, there's a few questions here. Just up to the top of this page in part C, there's a question about like, what is this T star that I introduced? Yeah, maybe that notation was a little confusing, but really what I was trying to denote is that we were asked to calculate the charge that has flowed after a certain amount of time. And over that amount of time, the loop has fallen a height of h. So what we wanted to do is somehow integrate our expression for current with respect to time over that magic amount of time during which the loop has fallen a height of h. So t is just kind of like a variable, but it's like we're integrating from t equals 0 to some time after which the loop has fallen a height of h. So that's what T star is. There's a question about the flux and using it to figure out Lenz's law. And I'll just read the question out because it's a good one. So do we always assume that flux is in the same direction as the external magnetic field? And I read it out like that on purpose because it's a really good question. Magnetic flux itself is not a vector quantity, right? It's a scalar quantity, B dot A. The dot product of two vectors is a scalar. So flux is not a vector mathematically, but it's really helpful to think of it as a vector. And thinking of it as a vector, in this problem, we've got an external magnetic field into the page. So let's say into the camera towards you, right? Into the page. And imagine that that magnetic field vector represented by a flux vector is getting shorter with respect to time. To oppose that change, the induced current creates its own magnetic field also into the page to oppose that change. So your question's a good one. Flux is not mathematically a vector, but it's really helpful to think of it as a vector and think of it as pointing in the same direction as that external field. And then think about how that's changing with respect to time. Is it getting bigger or smaller with respect to time? And then point your thumb in the direction that's necessary to oppose that change. That's a really good question. There's a question here about like, why is this loop moving at all? The loop is moving in general because from Newton's second law, I'm just going to annotate here in red so it's really clear, right? We could choose up or down to be positive, it doesn't really matter, but if we choose down to be positive, then we'll have mg down minus a time varying magnetic force up equals a net force downwards. And after a certain amount of time, once the upwards magnetic force that opposes motion gets big enough that it's equal and opposite to the weight of the loop, mg, the loop will reach a terminal speed. It's still moving downwards, but it's not accelerating anymore. That's Newton's second law. Yeah, and there's a really good question, and I like this question. I like the way you're thinking. Like, what could we have done for this part, for part D, if you didn't get the answer to part A? And I like the way you're thinking because this is a really good way to attack your exam, right? Like, how do I get the most part marks? Which parts of the question can I draw on to get part marks, right? This one's tricky because I'm just going to use my highlighter here. The current is a function of time. Or another way of saying that, the current is a function of the velocity of the loop. And so to get any further than this line that I'm highlighting, you'd have to have an expression for how the current is varying as a function of speed. Let's just pause for a second, right? You could probably make it to that line of algebra that I've highlighted because you could get the sense that there must be equal and opposite forces if we're at terminal speed. There's a weight force mg down and there's an opposing magnetic force up, right? So you could probably get that far just from that notion of a terminal speed and equal and opposite forces. But take a look at what this term is. I'm just going to highlight this. And I'm going to annotate over on the right here. Remember, for motional EMF, the induced EMF is BWV. We've seen that equation a few times now. And we haven't noted that it's time dependent the way it's written here, right? We haven't noted that the speed is dependent on time or any other things are dependent on time, right? But we've seen that equation a few times. And if you rearrange that, it just kind of magically works out that in this case, at the instant the terminal speed is reached, a certain amount of current is flowing. And you could plug that in to that term for the current. I really, really like your question because it's in the spirit of how do we get the most marks on this exam? And if you hadn't solved part A, you actually could still solve part D using this notion of motional EMF that we've seen a few times now. That's a really good question. I like it. All right, I'll just pause there and see if there's other questions. I've seen variations of this question a few times over the years, and it's a good one to look at. I'm just going to make one more note here on this page, and I'm going to write it in blue at the very bottom of the page. Another good problem to look at and it's on page 271 of your booklet, or it's page 8 of your exam package. And it has to do with a moving slide wire, like a moving conductor on a resistive circuit. And it's very, very similar to this one. And once you've done this one, and once you've done that multiple choice on motional EMF, you should recognize that situation right away and you should be able to solve it. So make sure to look at that one when you're studying. I want to do one last long answer problem. And let's go to page 291 now of your booklet. Page 291. And there's some room there for this long answer problem that's on page 102 in your exam package. So we're on page 291 and page 102. Okay, once you find this problem on page 102, it should look like this one on the screen. I'm just trying to line it up here. There we go. I'll give you guys a moment to read this one over and we'll work through this one together. Okay, let's look this one over together. So there's a square loop with the resistance big R, side length A, and it carries a steady current, I1. And you can see in the diagram, there's the loop, the square loop, and it's got a current I1 that's flowing in it, and steady, I guess, meaning constant with respect to time. And the center of that loop is located at a distance d from this infinitely long wire that's carrying a current I2. So terminology-wise, we've got a loop and a wire. A steady current I1 in the loop and a current I2 in the wire. Okay. Now, here's a really important sentence. Suppose that the current I1 is produced as a result of the current I2 changing with time. Let's just pause for a second and ask ourselves why that might be happening. The long straight wire carrying a current I2 creates a magnetic field around it. To figure out what that field looks like, point your thumb in the direction of I2, so up in the page, curl your fingers around the long straight wire, and you get the sense that there's a magnetic field into the page. We could call it B2 if you want. That's a result of the current I2 in that long straight wire. And if that current I2 is changing with respect to time, then that magnetic field B2 is changing with respect to time. That magnetic field B2 has a certain flux through the square area of that loop. And that time-varying flux would cause a current to flow. And we could use Lenz's law to convince ourselves what direction the induced current I1 in the loop would flow. Imagine the external magnetic field B2 pointing into the page. And if that current I2 is increasing with respect to time, then the flux into the page is increasing with respect to time. And to oppose that, the loop would create its own current and its own field out of the page and a counterclockwise current. The fact that the current I1 is flowing into the page means the current I2 must be reducing with respect to time. Okay, and if we take a look at parts A and B, what are we trying to do here? Part A is to get an expression for the flux between the loop and the wire. And part B is to get an expression for that current, I2. And we have to express all those things in terms of these other things. So this one's going to be a little bit tricky, a little bit mathematical. Let's go into our course booklet. We've got some room on page 291 here. And I'm going to try to draw a pretty big picture of what's happening here. Here's a current I2, which is a function of time. Here's that square loop. And just labeling some things on here, that square, the center of that square loop is a distance d from the wire. That loop has dimensions of A by A. We've realized that there must be a certain magnetic field, B2, into the page through the surface area of that loop. And we want to get an expression for the flux through that loop. And I've expressed it as B2 for a reason. That's the magnetic field created by the current I2. But there's a problem with this expression. B2 is the magnetic field created by a long straight wire, mu naught I2 over 2 pi r, the distance from the wire. So B2 is a function of distance from the wire, and that means the flux is a function of distance from the wire. And the only way to handle this, to get the total flux through that cross-sectional area, is to integrate. This is an expression for the bit of flux passing through that bit of area. So let's be a little bit more careful here. The bit of flux, a distance r from the wire. And actually, just to make this a little bit more intuitive, guys, I'm going to call this a distance x from the wire, a horizontal distance, is that field B2 multiplied by the little bit of area that it passes through, which is mu naught I2 over 2 pi x times the little bit of area that it passes through. And we could represent that by an a dx. And I'll show you what I mean on this diagram here. Suppose that there's a little strip of that loop's area with the width dx that's located at a distance x from that long straight wire. So this is the strength of the magnetic field B2 as a function of x, and this is the area of the strip, the vertical strip of that loop that it's passing through. I'm just going to pause there and see if there's any questions about that. And just zooming out a little bit from all this math for a sec, in all of these Faraday's law, flux induction problems, right? We've always started by writing that equation for the flux. We've always started by writing flux equals B dot A equals BA cos theta. And then we have to consider what's changing with respect to time. And in this case, the current I2 might be changing as a function of time, but not only that, the magnetic field created by that current depends on how far away you are from it. And so different vertical slices of that cross-sectional area of the loop are exposed to different strengths of magnetic field. And we've accounted for that in this expression. So there's the expression for the bit of flux passing through a vertical slice, a distance x from that wire. And to get the total flux, we have to integrate that. And some of those things are constants and some of them are variables. So to add up all the flux contributions from all those vertical slices at different distances across that square, we have to integrate dx over x. And the limits of this integral are from x equals d minus a over 2, that would be the left edge of the square, to d plus a over 2, that would be the right edge of the square. In terms of the geometry that they've given us, right? They told us this, the center of the square is a distance d from that long straight wire, and that the square has side length a. So that's the best way to express the geometric limits of that integral. And we know the integral of dx over x is ln x, so we could evaluate that integral. And so now we're evaluating ln x from d minus a over 2 to d plus a over 2. I'll just pause there for a sec before we evaluate that. There's a really good question that came on the Q&A. How come we're only considering the x direction and not considering what's happening in the vertical direction? The reason is, I'm going to highlight it on the screen here. The flux through the square loop is a result of the magnetic field created by that long straight wire, that current I2. And that's a function of the distance away from that wire. So since the wire and the square loop lie in the horizontal plane, the magnetic field a certain horizontal distance from the straight wire is constant for all values of y, I guess, for all values in the vertical axis of that square loop. It's really just horizontally that things are varying. That's a good question. Okay, so we've got to evaluate this integral. We're evaluating ln x from over those limits. So one step further here, that's mu naught I to a over 2 pi. And that's the ln of d plus a over 2 minus the ln of d minus a over 2. And you might remember that trick that we did yesterday. The difference of two lns is equal to the ln of the ratio. So I'm just going to go one step further here. We could write it like that, equivalently. And if we really wanted to, we could go one step further with that and just simplify. There's some factors of 2, right? You could take a cross multiple or a common denominator in the numerator and denominator of that factor of 2. And that's about as far as we can take that. So there's the first part of that question, getting an expression for the flux through that loop. And let's just pause for a second, take stock of what our equation has in it. So notice that our equation depends on the dimensions of the square, right? It depends on A. It also depends on D, the distance away from the straight wire we are. So that's kind of intuitive, right? It also depends on I2. So if the current through that long straight wire changes with respect to time, the flux will change with respect to time. And hopefully that's intuitive as well. The field created by that long straight wire depends on the current, and correspondingly, the flux depends on that current. All right, I'll just pause there and see if there's any questions. So we're done part A. We've got an expression for the flux. I'm going to skip over to the next page here. And on the next page, we can answer part B. And in part B, what we want to do is figure out how that current I2 is changing with respect to time. We're told that the current I1 is constant. So we were given, let's just make a note of that, given that I1 is constant with respect to time, and that current I1 is created as a result of the current I2 changing with respect to time. Faraday's law in electromagnetic induction is happening here. So let's write Faraday's law. The induced EMF, or the induced current, this is the way it appears on your formula sheet. And here we've got n equals 1 because we've got one loop, and this is just a notion of Lenz's law. So we could rearrange this and solve for the induced current, and technically we should be calling this current I1, right? This is the induced current in the loop as a result of the flux changing with respect to time. So let's rearrange and get an expression for I1. It's 1 over R times d phi dt. And we've got an expression for the flux. So let's plug that in here. We're looking for the rate of change of our expression from part A, mu naught I to A over 2 pi ln 2d plus A over 2d minus A. So we could evaluate that derivative and we get an expression for I1. Let's take that one step further. We want to take the derivative of the time derivative of everything inside that square bracket. A bunch of those things are constants, right? Mu naught, 2 pi, A, the side length of the square, that's a constant. Look at that ln function, ln 2d plus A. So that has to do with the square, the side length of the square and the distance the square is from the straight wire. Those are all constants as well. Let's pull all the constants out. And really, we're looking at the rate of change of the current I2 in the straight wire. And we are told in the question that that induced current I1 is constant. So if that whole expression is a constant, and if all the other things in that expression are a constant, that means that the current I2 is changing at a constant rate. We'll just pause there and see if there's any questions. Yeah, so there's a couple of good questions here. Just looking at the very top of the screen where we're using Faraday's law. And one question is, where did the 1 over r come from? So just to highlight, what we're interested in part B here is the current induced in the square loop. So we want to rearrange and solve for I1. And to do that, we're going to cross multiply this r down to the other side here. So there's the 1 over r. And there's another good question. Why did the negative sign go away? When you're using Faraday's law, that negative sign is just a reminder to use Lenz's law. It doesn't have to be in the rest of your math or the rest of your solution. It's just there as a matter of convention to remind us of the polarity of that induced current or induced EMF, such that Lenz's law is true, such that the induced current creates a field to oppose the changing flux. Okay, that's a mouthful. Okay, so we've figured out that the rate of change of the current I2 must be a constant. And what we want to do is somehow get an expression for that I2. Just looking back to the wording in the question, we want to get an expression for I2 somehow involving all of the other constants that were given. So we figured out from our math that di2 dt is a constant. I guess we could call that some other variable. I don't know, b, for lack of a better term. And that means the current I2 as a function of time is some initial value minus b times t. And I'm just going to annotate on here, I2 is decreasing with respect to time, since I1 is clockwise. And to understand that, we talked through that previously, but I'm just going to flash the question back up to make sure that we're clear on why that is. We're told in the question that the current I1 is clockwise. We're also told in the question that the current I2 flows upwards in our page. We're also told that the current I1 is induced by the magnetic field B2 created by that current I2 in the straight wire. So figuring out the magnetic field created by the straight wire, the thumb in the direction of the current I2, curling your fingers around that wire, that long straight wire, your fingers point into the page across the area of that wire loop. So the field B2, due to the current in the straight wire I2, is into the page. Let's do Lenz's law now. If that external field B2 is into the page, and if it's increasing with respect to time, the loop will create its own current and its own field that opposes that. It'll create a counterclockwise current and its own induced field out of the page to oppose that. But we're told that the current I2 is clockwise. And since that induced current is clockwise, it means the induced field is into the page in the same direction as that field B2. And the only way for that to be true is if the field B2 is decreasing with respect to time. In other words, the current I2 is decreasing with respect to time. So that's a real mouthful, right? And it's kind of hard to get all the cause and effect relationships there, but hopefully that's clear. So what we've got now is an expression for, sorry, I'm just going to flip to the last line of our algebra. We've got an expression for the current I2 as a function of time, and it's a decreasing function of time at some rate b, whatever that is. And from our earlier equation, we can express what b is. B is the rate of change of I2. So what we have to do is just invert this expression. The rate of change of the current I2 is, in terms of all the other variables given to us, now, how do we properly express that? You could substitute that rate of change, that b term, into the previous equation. But I think if you just put a box around this whole thing, that should be enough to get us full marks. We were asked for an expression for the current I2 as a function of time. We know it has to be decreasing with respect to time in order to cause that clockwise induced current I1 in the loop. And we've got an expression for the rate at which I2 is decreasing with respect to time. So there we go. That's the answer to part B. That question is probably the hardest you could make a question on Faraday's law and flux and induction. And I really wanted to do it. It's a good one for us to study because it highlights the importance that flux depends on the magnetic field. It also depends on the area exposed to magnetic field. And either of those things could be variable. And in this case, we had to realize that the magnetic field across the loop is not constant. with respect to distance away from that straight wire. All right. I'll just pause there and see if there's any questions on that one. All good? Okay, so just pause here and zoom out. I want to highlight a few things. In your course booklet, in chapter 1, there is a study list. You can use that as a little bit of a checklist as you're studying to make sure you're comfortable with all the different concepts. I'll just highlight where that is. That should be on, I think it's page 9 in section 1.7. So just a reminder that that's there. And we also reviewed chapter 9, which is a whole list of tips to help you guys get the most marks. In fact, to maximize your mark, you're looking for all the part marks you can get. And there's some good tips there in chapter 9 on how to do that. I'll also point out we've reviewed that summary of magnetic effects, that table. It's on page 198 of your booklet. And that's a really helpful kind of one-page summary of all the different types of questions you might run into. And we learned a heck of a lot about magnetism in a day and a half here. So I hope you guys found that helpful. And I wish you guys all the best of luck on your exam. I'll be checking the Facebook group in case you have any questions there. The solutions to all of those exam package problems have been posted already. And for lack of a better place to tell you, at the bottom of every page of the booklet, I've just highlighted that. You can go to the Course Cram website, go to your prep session page, and you should be able to find the solutions. And I'll be happy to answer your questions on the Facebook group. All right, guys, it's been a pleasure helping you all year through APSC 111 and 112. I wish you guys all the best of luck on your exam and on all your exams, and I wish you guys a good summer. Take care. Bye-bye.